So, here's something worth thinking about as you settle in tonight. Right now, in the walls around you, electrons are drifting through copper wire at roughly 1 millimeter per second. Slower than a snail. Slower than honey sliding off a spoon. And yet, the instant someone flips a switch in a power station hundreds of miles away, the lamp on your nightstand responds. Not in a second, not in a heartbeat, in a tiny fraction of a blink. That signal, that ripple of energy, races through the wire at nearly the speed of light. 186,000 miles every single second, while the electrons themselves barely crawl. And the reason that's possible, the reason a wave of energy can sprint through a wire while the actual particles inside it barely move, has to do with something invisible. Something that fills the space around that wire and every other wire and every magnet and every charged object in the universe. Something called a field, an electromagnetic field.
And here's what makes this story so extraordinary. For most of human history, nobody knew any of this. People saw lightning crack the sky and thought it was the anger of gods. They rubbed amber on fur and watched feathers leap toward it and thought the stone had a soul. They held a dark, heavy rock near a piece of iron and felt it pull, and they had no idea why. These things seemed completely unrelated. Lightning, amber tricks, magnets, the northern lights, the spark you get from a wool sweater in winter, the glow of a firefly, the way your heart beats in a steady rhythm without you ever asking it to. For thousands of years, each of these was its own separate mystery, its own isolated curiosity, filed away in its own drawer, explained by its own local myth. And then, slowly, painstakingly, over the course of about 3 centuries, something remarkable happened. People started discovering that these drawers weren't separate at all. They were connected.
The spark and the lightning were the same thing. The magnet and the electric current were the same thing. The light from a candle and the radio wave from a transmitter were the same thing. And eventually, even the force holding atoms together, and the force that causes certain kinds of radioactive decay, turned out to be, at a deep enough level, the same thing. The history of electricity and magnetism is really a history of unification, of walls falling down, of things that looked completely different turning out to be the same, seen from different angles. And every single time one of those walls came down, the world got simpler and stranger at the same time. Simpler because there were fewer separate forces to explain. Stranger because the connections were so unexpected that even the people who discovered them had trouble believing what they'd found. So tonight, I want to walk you through that story. All of it. Slowly, the way it actually unfolded, with all the wrong turns and arguments and moments of sheer bewilderment. We're going to follow a thread that stretches from a piece of fossilized tree sap in ancient Greece all the way to particle accelerators smashing atoms apart at nearly the speed of light. And along the way, we're going to watch walls come down, one by one. How did people figure out that the tiny crackle from a piece of rubbed amber and the terrifying bolt that splits a tree in half are the same phenomenon? How did a compass needle twitching near a battery wire lead to the discovery that electricity and magnetism, those two seemingly separate forces, are really one? How did a quiet Scottish mathematician, working alone with pen and paper, prove that light itself is an electromagnetic wave, and in doing so predict the existence of radio, microwaves, X-rays, and every other form of radiation decades before anyone detected them? And is there a deeper unity still? Could the electromagnetic force be just one face of something even more fundamental? A single master force that splinters into separate appearances, the way white light splinters into colors through a prism. Those are the questions we're going to sit with tonight. And if you drift off somewhere along the way, that's perfectly fine. The story will still be here. The connections will still be there in the morning, humming quietly in the wires, glowing softly in the light, holding the atoms of your body together while you sleep. Let's begin where it always begins, with something small and strange and unexplained, with amber. About 2,600 years ago, on the coast of what is now Western Turkey, there was a city called Miletus, a prosperous trading port full of merchants and sailors and the kind of restless, curious people who thrive in places where different cultures bump up against each other. And in that city lived a man named Thales, who is sometimes called the first philosopher of the Western world, which is a grand title, but in Thales's case, not entirely undeserved. Because what made Thales unusual, what set him apart from the priests and storytellers who came before him, was a very specific stubbornness. He refused to accept "the gods did it" as an explanation for natural phenomena. When he saw something strange happen, he wanted a mechanical reason, a physical cause, something you could test and argue about. And Thales noticed two strange things. The first involved amber. Amber is fossilized tree resin, a beautiful golden-brown stone that the Greeks used for jewelry. They called it electron. And if you took a piece of amber and rubbed it briskly against a piece of fur, something eerie happened. Small, light objects, bits of straw, flecks of dust, tiny feathers, would leap toward the amber and cling to it, as if the stone were reaching out with invisible fingers. It looked almost alive. In fact, Thales reportedly suggested that amber must have a kind of soul, since it could move things without touching them. The second strange thing Thales noticed involved a completely different material: lodestone. Lodestone is a naturally magnetized mineral, a dark, heavy rock that you can find in certain deposits. And lodestone does something equally mysterious. It attracts iron. Bring a piece of lodestone near an iron nail, and the nail jumps toward it, clings to it, holds on. And if you hang a piece of lodestone from a string, it slowly rotates until it points roughly north. Two invisible forces, two materials that could reach across empty space and pull things toward them. And Thales, as far as we can tell, thought these were both fascinating, both worth recording, but entirely separate phenomena. The amber trick and the lodestone trick had nothing to do with each other. They just happened to share the superficial feature of attraction at a distance. But here's the thing. That's how things stood. For a very, very long time. Not decades, not centuries, millennia. For roughly 2,000 years after Thales, the amber effect and the lodestone effect lived in separate categories in the human mind. If you had asked a scholar in the year 1500 whether electricity and magnetism were related, they would have looked at you blankly. Why would they be? One involved rubbing stones and getting sparks. The other involved dark rocks that pointed north. Those are obviously different things. Now there's a reason the connection took so long to find, and it's worth pausing to appreciate it, because it tells you something important about how science works. The amber effect, what we now call static electricity, was tiny. It was a parlor curiosity. You could pick up a feather with it, maybe get a little crackle, but you couldn't do anything useful. You couldn't light a fire with it. You couldn't move heavy objects. And it vanished, almost as quickly as it appeared. Rub the amber, attract some straw, and within moments, the effect faded. Meanwhile, lodestone was a bit more practical. People eventually figured out that a magnetized needle could serve as a compass, and compasses became essential for navigation, especially at sea. But even then, nobody understood why a compass pointed north. They just knew it did and used it accordingly. So you had two faint, fleeting, poorly understood phenomena, and the idea that they might be deeply connected was, frankly, not a thought that had any reason to occur to anyone. That's the thing about unification in science. The connections are often invisible, precisely because the phenomena look so different on the surface. It takes a very specific set of circumstances, usually a new tool, a new technique, or a new way of thinking, to reveal the hidden thread. The first person to draw a really clear line between the Ampère effect and the lodestone effect, to give each one its own proper identity and insist that they be studied on their own terms, was an Englishman named William Gilbert. Gilbert was a physician, the personal doctor to Queen Elizabeth I, which was a pretty good gig in the late 1500s. But his real passion wasn't medicine, it was magnets. In 1600, he published a book called De Magnete, which is Latin for On the Magnet, and it was the most thorough study of magnetism anyone had ever produced. Gilbert did something crucial. He built a small spherical lodestone, which he called a terrella, a little earth, and he showed that the way a compass needle behaves on the surface of this little sphere is exactly the way a compass behaves on the surface of the actual Earth. The conclusion was striking. The Earth itself must be a giant magnet. That's why compasses point north. Not because of a magnetic mountain at the North Pole, which was one popular theory, and not because of the North Star, which was another. The planet has magnetic poles, just like the lodestone. But Gilbert also spent a lot of time experimenting with the Ampère effect, and he discovered that it wasn't just amber that could attract things when rubbed. Glass, sulfur, sealing wax, and many other materials could do it too. He coined the word electrics, from the Greek electron, to describe materials that exhibited this behavior. And he drew a careful distinction between the electric force and the magnetic force. They looked similar on the surface, both involved attraction at a distance, but Gilbert insisted they were fundamentally different. Electrics needed rubbing to activate. Magnets worked all the time. Electrics attracted everything light enough. Magnets only attracted iron and a few other metals. Electrics lost their power quickly. Magnets kept theirs indefinitely. Gilbert was right to separate them, at least at that stage of understanding. You have to understand the parts before you can see how they connect. And by giving the electric force its own name, its own category, its own set of experiments, he effectively created the field of electrical science. Before Gilbert, electricity was just that thing amber does. After Gilbert, it was a subject worthy of systematic investigation. The centuries between Gilbert and Franklin are sometimes glossed over in the history of electricity, but they matter because they illustrate something important about how science progresses. It doesn't move in a straight line. It wanders, it backtracks. It gets distracted by dead ends and seduced by spectacular demonstrations that look like progress, but aren't. The 17th and early 18th centuries were, for electricity, a period of accumulation without understanding. People were gathering the raw materials that Franklin would eventually assemble into a theory. But they didn't know that's what they were doing. One of the most significant figures of this era was Otto von Guericke, a German engineer and politician who is mostly remembered for his dramatic demonstrations of vacuum with the Magdeburg hemispheres, two bronze half-spheres pressed together with the air pumped out, which teams of horses couldn't pull apart. But von Guericke also built the first electrostatic generator around 1663. It was a ball of sulfur, about the size of a child's head, mounted on an axle so it could be rotated by hand. When he pressed his palm against the spinning ball, friction transferred charge from his hand to the sulfur, and the charged ball could then attract feathers, paper scraps, and other light objects. Von Guericke's machine was crude by later standards, but it was the first device that could produce electrical effects on demand, without rubbing individual pieces of amber. It was an electrical factory, tiny and primitive, but a factory nonetheless. And over the next century, experimenters across Europe refined the design, replacing the sulfur ball with glass cylinders or discs, adding leather pads and metal collectors, building ever larger and more powerful friction machines that could generate impressive sparks and charge multiple people simultaneously. An Englishman named Stephen Gray, working at the Charterhouse in London in the early 1720s, made a discovery that seems obvious in hindsight, but was genuinely revolutionary at the time. He showed that electrical charge could be transmitted from one place to another through certain materials, and that other materials blocked the transmission. He discovered, in other words, the distinction between conductors and insulators. Gray demonstrated this by suspending a boy on silk ropes, which acted as insulators, and connecting him to a friction machine with a brass wire. Charge flowed along the wire and into the boy's body, where it accumulated because the silk ropes prevented it from draining away into the ground. The boy could then attract feathers and scraps of metal leaf with his fingers and even produce small sparks from his nose, to the delight of audiences. It was science as entertainment, absolutely. But it was also genuine discovery. The realization that some materials allow charge to flow freely while others trap it in place is fundamental to every electrical circuit ever built. Every wire, every switch, every insulator on every power line, every plastic coating on every cable in your house relies on the distinction Gray discovered in a room at the Charterhouse by dangling a small boy from the ceiling. A French chemist named Charles-François de Cisternay-Dufay carried the investigation further. In the 1730s, Dufay showed that there appeared to be two kinds of electrical charge, which he called vitreous and resinous, because one was produced by rubbing glass and the other by rubbing resin. Objects carrying the same type of charge repelled each other. Objects carrying opposite types attracted each other. This two-fluid theory, the idea that electricity consisted of two distinct substances, became the standard framework for understanding electrical phenomena in Europe for the next 2 decades. And it was this two-fluid theory that Franklin would demolish with his single-fluid model in the 1740s. Dufay's vitreous and resinous electricity were not two different substances. They were excess and deficit of a single substance, positive and negative. Two states, not two materials. Franklin's simplification was more than aesthetic. It carried explanatory power. It explained the Leyden jar. It explained conservation of charge. It explained why charge always seems to come in equal and opposite amounts. You can't produce positive charge somewhere without producing an equal amount of negative charge somewhere else, because all you're doing is redistributing a fixed total. Franklin had found a deeper truth beneath Dufay's carefully observed facts. This is a pattern that repeats throughout the history of science, and it's one of the recurring themes of our story tonight. Careful observation comes first. Then classification, the sorting of phenomena into categories. Then unification, the discovery that the categories are artificial, that what looked like separate kinds are really one kind manifesting in different ways. Dufay observed and classified, Franklin unified. Both contributions were essential. You can't skip straight to unification without first having something to unify. But the investigation moved slowly. Through the 1600s, electrical experiments were mostly the province of showmen and hobbyists. People built friction machines,
devices that could generate static electricity by spinning a glass ball or disc against a pad of leather or cloth. The sparks were bigger than what you could get from rubbed amber, and they were entertaining. Electricity became a popular spectacle. Traveling lecturers would charge volunteers on insulated platforms and make their hair stand on end, or shoot sparks from their fingertips, or light small amounts of alcohol on fire with an electrical discharge. It was science as theatre. And then, in the middle of the 1740s, someone accidentally invented something that changed everything. And the word accidentally matters here, because the discovery of the Leyden jar is one of those beautiful moments in science where a mistake opens a door that nobody even knew was there. It happened in Leiden, in the Netherlands.
A professor named Peter van Musschenbroek was trying to figure out how to store electrical charge. The prevailing metaphor at the time was that electricity was some kind of fluid, so Musschenbroek thought, reasonably enough, that if electricity is a fluid, maybe you can store it in a jar, the way you store water. He took a glass jar, filled it partly with water, stuck a metal wire through a cork in the top, connected the wire to a friction machine, and cranked the machine, trying to pour electrical fluid into the jar. Then he touched the wire with one hand while holding the jar with the other. The shock nearly knocked him off his feet. He wrote to a colleague that he wouldn't repeat the experience for the entire Kingdom of France. What Musschenbroek had built, without fully understanding it, was the first capacitor, the first device that could store a significant amount of electrical charge and release it all at once.
The glass of the jar was acting as an insulator, separating two conducting surfaces, the water on the inside and Musschenbroek's hand on the outside, and charge was accumulating on both sides, held apart by the glass, building up, until the circuit was completed through his body, and all that stored energy released in a single violent pulse. The Leyden jar, as it came to be called, was a genuine breakthrough, and not just because it could knock a professor sideways. For the first time, experimenters had a way to accumulate and store a substantial amount of electrical charge. Before the Leyden jar, all you had was the feeble trickle from a friction machine. Now, you could save that trickle up over time and release it as a powerful jolt. You could make sparks inches long. You could send shocks through chains of people, dozens of them, hundreds even, all jumping at the same instant.
A French showman named Abbé Nollet discharged a Leyden jar through a line of 180 soldiers in front of King Louis XV. They all leaped simultaneously. The king thought it was hilarious. But beneath the spectacle, something deeper was happening. Electricity was graduating from a curiosity to a force. Something with real power, something worth taking seriously, something that demanded explanation. And the person who would provide the most coherent explanation, the person who would take this scattered collection of sparks and shocks and party tricks and weave them into the first real theory of electricity, was working not in a European university or a royal court, but in a print shop in Philadelphia. Benjamin Franklin. And what Franklin was about to figure out would be the first great unification in this story.
The realization that all these different electrical phenomena, the amber tricks, the sparks, the Leyden jar shocks, the lightning in a thunderstorm, were not separate things at all. They were the same force, the same substance, the same phenomenon, manifesting in different ways. Franklin came to electricity almost by chance. Around 1746, a friend in London sent him some electrical equipment, a glass tube for generating static charge, and a few other odds and ends. Franklin was already in his 40s, already wealthy, already famous as a publisher and civic organizer. He had no formal scientific training. He'd never been to a university. But he had something that turned out to matter a great deal more than credentials. He had an extraordinarily clear mind and an absolute refusal to accept explanations that didn't make sense to him. At the time, The prevailing theory about electricity was that there were two different electrical fluids, sometimes called vitreous and resinous electricity. The idea was that rubbing glass produced one kind of electrical substance and rubbing resin produced another, and these two substances attracted each other and repelled their own kind. It was a reasonable enough theory, but Franklin thought it was unnecessarily complicated. He proposed something much simpler. There's one electrical fluid, not two. Every object has a natural amount of it. When you rub amber on fur, you're not creating electricity, you're moving it. The amber gains some of the fluid, ending up with more than its natural share, and the fur loses some, ending up with less. The object with an excess Franklin called positive. The object with a deficit he called negative. And the attraction between a positively charged object and a negatively charged one is simply the fluid trying to redistribute itself, trying to reach equilibrium, flowing from where there's too much to where there's too little. Think about what that means. With one stroke, Franklin replaced a confusing two-fluid theory with a clean, elegant, single-fluid model. And embedded in that model was something genuinely profound, something Franklin grasped intuitively, even though it wouldn't be formally stated for another century. Charge is conserved. You can't create it from nothing, and you can't destroy it. You can only move it from one place to another. The total amount of electrical fluid in a closed system never changes. It just redistributes. This was the first unification. Not between electricity and magnetism, we're not there yet, but within electricity itself. Franklin unified all the scattered electrical phenomena, the amber tricks, the sparks from friction machines, the shocks from Leyden jars, into a single framework. One substance, one set of rules, excess or deficit, flow from high to low, conservation. But here's the thing. Franklin got one detail wrong, and it's a small irony that has confused every physics student since. He guessed that the electrical fluid flowed from positive to negative. Centuries later, we discovered that what actually moves in a wire is electrons, which carry negative charge, and they flow from negative to positive, the opposite direction from what Franklin assumed. His convention was backwards. But by the time anyone figured this out, the convention was so deeply embedded in every scientific paper, every diagram, every equation, that it was easier to live with it than to change it. So today, when an electrician talks about current flowing from positive to negative, that's Franklin's convention. And it's technically describing the motion of a fictional positive fluid rather than the actual motion of real electrons. It's one of those historical accidents that gets baked into the fabric of a discipline so thoroughly that removing it would cause more confusion than keeping it. But the core of Franklin's insight, the one fluid theory, conservation of charge, the idea that positive and negative are just two states of the same thing, that was right. And it was powerful. And then Franklin did something reckless and brilliant that turned him from a colonial amateur into the most famous scientist in the world. He proved that lightning is electricity. The popular image is Franklin standing in a field flying a kite in a thunderstorm, which makes it sound like a charming folk tale. In reality, it was genuinely dangerous. In June of 1752, Franklin flew a kite during a thunderstorm, with a metal key tied to the string near the bottom. The string got wet from rain, making it conductive. When he brought his knuckle near the key, he got a spark. He then charged a Leyden jar from the key, proving that the charge from the sky behaved identically to the charge from his friction machines. A Russian physicist named Georg Wilhelm Richmann tried a similar experiment the following year in St. Petersburg. A ball of electrical charge traveled down his apparatus and struck him in the forehead. He died instantly. He was the first person known to have been killed while conducting electrical experiments. So when we talk about Franklin and his kite, it's worth remembering the stakes. He wasn't performing a cute demonstration, He was testing a hypothesis that could have killed him. And the hypothesis turned out to be correct. Lightning, that terrifying, godlike force that had been attributed to divine anger for all of human history, was just electricity. The same stuff you get from rubbing amber, the same stuff stored in a Leyden jar, scaled up enormously, moving with incredible violence, but fundamentally the same phenomenon. That was a staggering realization. Nature's most dramatic display of power, the thing that split trees and set buildings on fire and killed people where they stood, was made of the same substance as the feeble crackle from a piece of rubbed glass. The drawer labeled lightning and the drawer labeled static electricity turned out to contain the same thing. The first wall had come down, and Franklin, being the practical man he was, immediately turned the discovery into something useful. If lightning is electricity, and electricity follows predictable paths, seeking the easiest route to ground, then you can protect buildings. Put a pointed metal rod on the roof, connect it to a thick wire, run the wire into the ground. Lightning strikes the rod, flows harmlessly down the wire, and the building survives. The lightning rod. One of the first practical applications of electrical science, and it saved an incalculable number of lives over the centuries that followed. But Franklin's work, monumental as it was, still left enormous questions unanswered. He could accumulate charge, he could move it, he could describe its behavior in broad terms, but he couldn't produce a steady, continuous flow of electricity. Everything was still static. You charged something up, it discharged in a burst, and that was it. The Leyden jar gave you one big jolt, and then it was empty. The friction machine gave you a trickle of sparks, but nothing you could sustain.
To get from parlor tricks and lightning rods to anything resembling the electrical world we live in today, someone needed to figure out how to make electricity flow continuously, like water through a pipe. And that breakthrough came from one of the strangest feuds in the history of science. A fight between an anatomist and a physicist, conducted through the medium of dead frogs. The anatomist was Luigi Galvani. He was a professor at the University of Bologna, and sometime around 1780, while dissecting frogs, which was perfectly normal for an anatomist of the era, he noticed something peculiar. When a metal scalpel touched the leg of a dead frog near an electrostatic machine that happened to be sparking nearby, the leg twitched violently, as if the frog were trying to jump. The dead frog's muscles contracted, hard, and then relaxed. But here's the thing. Galvani was fascinated. He spent years investigating, trying different conditions, different metals, different configurations, and he eventually concluded that the frog's muscles contained their own inherent electricity, a special kind of electrical fluid that he called animal electricity. The muscles, in his view, were like biological Leyden jars, storing up charge and releasing it to produce motion. Life itself, Galvani believed, was fundamentally electrical. Now, there was a physicist at the University of Pavia, about 90 miles from Bologna, who read Galvani's results with great interest and then growing skepticism. His name was Alessandro Volta, and Volta noticed something that Galvani had glossed over. The twitching was strongest and sometimes only worked at all when two different metals were involved. Touch the frog with the same metal on both ends, and the effect was weak or absent. Use two different metals, say copper and zinc, and the legs kicked vigorously. But here's the thing. Volta had an entirely different interpretation. He thought the frog wasn't the source of the electricity at all. The frog was just a very sensitive detector, a biological instrument. The actual electricity was being generated by the contact between the two different metals. The frog wasn't the battery. The frog was the meter. This launched one of the bitterest scientific rivalries of the late 18th century. Galvani and his followers insisted animal electricity was real, that living tissue generated its own electrical fluid. Volta and his camp argued that the electricity was coming from the metals, and that the frog was simply reacting to an external current. Papers were published, reputations were staked. It got personal. The truth, as we now understand it, is that they were both partially right. Volta was correct that the junction between two different metals generates a voltage. But Galvani wasn't entirely wrong either. Biological cells really do generate electrical potentials. Your neurons are firing right now, as you lie there, using tiny voltage differences across their membranes to carry signals through your nervous system. The electrical activity of your heart is what an electrocardiogram measures. Animal electricity is real. Galvani just had the mechanism wrong in his specific experiments, where most of the electricity was indeed coming from the metals. But here's what matters for our story. Volta's determination to prove Galvani wrong drove him to build something that changed the world. Because if the electricity was coming from the contact between two different metals, Volta reasoned, then you shouldn't need a frog at all. You should be able to produce electricity just by stacking metals together with something wet between them. And that's exactly what he did. Around 1799, Volta built a device that was almost absurdly simple.
He took a small disc of zinc and a small disc of copper and placed between them a piece of cardboard soaked in salt water. Then he stacked another zinc disc, another wet cardboard, another copper disc, and so on, building a tower of alternating metals with wet separators between each pair. And when he connected a wire from the bottom of the stack to the top, electricity flowed. Not a spark, not a jolt, a steady, continuous current, flowing for as long as the chemical reactions in the pile could sustain it. Think about what Volta had just given the world. For the entire history of electrical science up to that point, every bit of electricity anyone had ever produced was static, charge that built up and then discharged in a single burst. But Volta's pile, announced in a letter to the Royal Society of London in March of 1800, provided something completely new. A river instead of a splash. A sustained, controllable flow of electrical current.
He called it a pile because it was literally a pile of disks. We know it as the voltaic pile, the world's first true battery. And the unit of electrical potential difference, the volt, carries his name to this day. The impact was immediate. Within weeks, scientists across Europe were building their own piles and doing things that would have been unimaginable with static electricity. Two English chemists, William Nicholson and Anthony Carlisle, connected wires from a voltaic pile to a container of water, and the water began to bubble. At one wire, hydrogen gas formed, at the other, oxygen. They had split water into its constituent elements using electricity. Electrolysis, as it came to be called, revealed something startling. Chemical bonds, the forces that held molecules together, were fundamentally electrical in nature. Electricity could rip atoms apart. A young chemist named Humphrey Davy at the Royal Institution in London took this technique and ran with it spectacularly.
He built bigger and bigger voltaic piles and used them to decompose substances that no other method had been able to break apart. In 1807, he passed current through molten potassium hydroxide, and tiny globules of a shiny silvery metal appeared at one electrode. He had isolated potassium, an element so reactive it had never existed in pure form in nature. His assistant later reported that Davy was so excited he danced around the laboratory. Within days, he had isolated sodium using the same method, and over the following years, electrolysis yielded barium, strontium, calcium, magnesium, element after element, torn free from compounds that had resisted every other approach. Electricity had gone from a parlor curiosity to a tool that could unlock the fundamental structure of matter. The second great unification within electricity was now complete.
Static electricity and current electricity, the spark from a Leyden jar and the steady flow from a voltaic pile were the same underlying phenomenon, electrical charge, manifesting in two different modes. One was a sudden, violent discharge. The other was a calm, continuous stream. But the substance flowing was the same. Franklin's electrical fluid, whether released all at once or trickled out steadily, was one thing. Let me linger on the voltaic pile for a moment longer, because its impact on the world is hard to overstate, and the speed with which that impact unfolded is one of the most remarkable episodes in the history of technology. Volta announced his invention in March of 1800. By April, laboratories across Europe were building their own piles. By May, Nicholson and Carlisle had used one to decompose water. By the end of the year, scientists were using voltaic piles to pass current through every substance they could get their hands on, watching to see what happened. The pace of discovery was intoxicating. After centuries of playing with static charges and getting nothing but sparks and shocks, the scientific world suddenly had a continuous, controllable river of electricity. And the things you could do with it were extraordinary. Humphrey Davy, who had an instinct for the spectacular and a gift for public communication that made him the most popular lecturer in London, built bigger and bigger piles. His greatest battery at the Royal Institution consisted of 2,000 pairs of metal plates, occupying an entire room, and could deliver enough current to produce blinding arcs of light between carbon rods. This arc light, first demonstrated publicly in 1809, was the most intense artificial light the world had ever seen. It was too bright for domestic use, far too bright. You could barely look at it, but it would eventually find applications in lighthouses, in theatrical spotlights, and in street lighting. The electric arc was the first glimpse of a world illuminated by electricity rather than flame, and the chemistry kept coming. Davy's protégé, Faraday, would later formulate the laws of electrolysis, showing that the amount of substance deposited or dissolved at an electrode is directly proportional to the total charge passed through the solution. This was a quantitative relationship between chemistry and electricity, one of the first precise, measurable links between two domains of science that had previously been considered separate. Faraday's laws of electrolysis were among the first hints that matter itself is fundamentally electrical in nature, that the forces binding atoms into molecules and molecules into substances are electromagnetic. That hint would be fully confirmed only a century later with the development of quantum mechanics and the understanding that chemical bonds are the result of electromagnetic interactions between the electron clouds of adjacent atoms. But in the early 1800s, nobody knew about electrons or quantum mechanics or atomic orbitals. All they knew was that electricity could rip apart substances that no other force could divide, and that the amount of electricity needed was precisely proportional to the amount of substance liberated. electricity and chemistry were quantitatively linked. Another wall was crumbling, another boundary between apparently separate domains dissolving under the steady pressure of experimental evidence. By 1820, the voltaic pile had transformed the landscape of science. It had made possible the discovery of new elements, the decomposition of water, the production of arc lights, the study of electrochemistry, and the accumulation of enormous quantities of experimental data about how electric currents behave in different materials. It had turned electricity from a curiosity into a tool, and scientists were racing to find out what else this tool could do. And then, in the spring of that year, in Copenhagen, Ørsted's compass needle twitched, and the tool that had been unlocking chemistry was about to unlock something much deeper: the connection between electricity and magnetism. The second great unification was about to begin, triggered by a wire, a battery, and a compass sitting together on a lecture table. Now, there's something about the voltaic pile that I think is worth appreciating more fully, because it illustrates a principle that runs through the entire history of electricity. The pile was not just a new device, it was a new mode of access. Before Volta, every electrical experiment was a race against time. You built up charge on a friction machine or in a Leyden jar, and you had seconds, maybe minutes, to work with it before it leaked away. Every experiment was a sprint. Every observation had to be grabbed in the moment before the charge dissipated. The pile changed the tempo of electrical science.
Suddenly, you could sit down with a steady current and study it at leisure. You could observe effects over hours instead of seconds. You could measure things carefully, repeat them, adjust them, refine them. The pile didn't just give scientists more electricity, it gave them more time. And time, in science, is everything. The ability to repeat an experiment slowly and carefully, varying one thing at a time, is what separates casual observation from systematic understanding. Volta's pile made that possible for electricity for the first time, and the chemical nature of the pile revealed something else. Electricity was not just a property of rubbed amber or charged metal spheres. It was embedded in the structure of matter itself. The chemical reactions that drove the pile were happening at the atomic level, at the surfaces where zinc met salt water, where copper ions took up or released electrons.
The pile was a window into the atomic world, and the electricity it produced was a signal from that world, a message from the invisible interior of matter saying, "We are electrical beings, all the way down." Within a few decades of Volta's announcement, Faraday would formulate his laws of electrolysis, showing a precise, quantitative relationship between the amount of electric charge passed through a solution and the amount of chemical substance deposited at the electrodes. Faraday introduced the terms electrode, anode, cathode, ion, and electrolyte, vocabulary that is still used in every chemistry and physics classroom today. And his laws hinted at something that wouldn't be fully understood for another half-century: that electric charge comes in discrete units, in little indivisible packets, each one associated with a single atom. Those packets are what we now call electrons.
And their discovery by J.J. Thomson in 1897 would vindicate both Franklin's one-fluid theory and Faraday's quantitative laws of electrolysis, showing that the electrical fluid was actually a stream of tiny identical particles, each carrying an identical charge. But we're getting ahead of ourselves. In the first decades of the 19th century, the electron was still unknown, quantum mechanics was undreamed of, and the atomic theory itself was still controversial. What mattered at the time was that the voltaic pile had given scientists something they desperately needed: a reliable, steady, controllable source of electric current. And with that current flowing, experiments that had been impossible became routine, and the questions that had been unanswerable became answerable. And one of the most important of those questions, the one that would shake the foundations of physics and reveal the next great unification, was about to be answered by a compass needle sitting on a table in Copenhagen, twitching in the presence of a wire carrying current from a voltaic pile. And yet, through all of this, through Thales and Gilbert and Franklin and Volta, through sparks and shocks and dancing professors and dead frogs and piles of zinc and copper, one wall was still firmly standing. The wall between electricity and magnetism. Nobody had any particular reason to think these two forces were connected. Electricity came from rubbing things or from chemical reactions in batteries. Magnetism came from lodestones and iron. They looked different. They behaved differently. They came from different sources. Yes, a few people had noticed odd things. Sailors occasionally reported that a lightning strike could magnetize their compass needles. A compass might behave strangely during a thunderstorm. But these were isolated anecdotes, curiosities within curiosities, nothing anyone could build a theory on. And then, on a spring day in 1820, in a lecture hall at the University of Copenhagen, the wall came down. And the man who knocked it down wasn't even trying to. He was just giving a lecture, demonstrating the heating effect of an electric current, when he glanced at a compass sitting on the table near his wire. And the needle moved. His name was Hans Christian Ørsted. He was Danish, born in 1777, the son of a pharmacist, and he had spent years thinking about whether electricity and magnetism might be related. He wasn't the first to wonder.
The German philosopher Friedrich Schelling and others in the Romantic Naturphilosophie movement had argued on purely philosophical grounds that all forces of nature must be connected, that the universe was a unity, that what appeared as separate forces were just different expressions of one underlying power. Ørsted was sympathetic to this view. He had even published a few speculative papers suggesting that electricity and magnetism might share a common origin. But speculation is cheap. What Ørsted needed was evidence. And on that spring day, he got it. He had a wire connected to a voltaic pile carrying a current and a compass needle sitting nearby on the lecture table. When the current flowed through the wire, the compass needle deflected. It swung away from pointing north and oriented itself roughly perpendicular to the wire. Now, there is some debate among historians about whether this was a genuine surprise or whether Ørsted had been deliberately looking for this effect.
Some accounts paint it as pure serendipity, a chance observation during a routine lecture. Others suggest he had been trying the experiment privately and gotten ambiguous results, and that the lecture was a more careful attempt. Either way, what he observed was unmistakable. An electric current flowing through a wire was exerting a force on a magnetic needle. Electricity was producing magnetism. Ørsted spent the next several months carefully characterizing the effect. He found that the force wasn't a simple push or pull, like Coulomb's electric force or Newton's gravity. The compass needle didn't point toward the wire or away from it. It pointed around the wire, tangentially, as if the magnetic influence was circling the conductor, like a current flowing in an invisible river around the wire. He published his results in July of 1820 in a brief Latin paper that he sent to scientific journals and colleagues across Europe. The response was electric, if you'll forgive the pun. Within weeks, laboratories from Paris to London to St. Petersburg were replicating Ørsted's experiment, and the scientific world was buzzing. For the first time in history, someone had demonstrated a clean, repeatable, undeniable connection between electricity and magnetism. And the person who moved fastest, who seized Ørsted's result and drove it furthest in the shortest time, was a French physicist with one of the most remarkable and most tragic stories in all of science. His name was André-Marie Ampère. Ampère was born in Lyon in 1775. He was largely self-educated, a prodigy who supposedly mastered advanced mathematics by reading through the volumes of the Encyclopédie as a child. His personal life was marked by devastating loss.
His father was executed during the French Revolution, guillotined in Lyon in 1793, and the event shattered the young Ampère so profoundly that he reportedly didn't speak for a year afterward. His wife, Julie, whom he loved deeply, died in 1803 after a long illness, and Ampère carried that grief for the rest of his life. He was brilliant, tortured, restless, and frequently unhappy. And when he heard about Ørsted's compass needle, he dropped everything. Within a single feverish week in September of 1820, Ampère had replicated Ørsted's experiment, extended it, and asked a question that Ørsted hadn't addressed. If a current-carrying wire produces a magnetic effect, what happens when you put two current-carrying wires next to each other? Do they interact? They absolutely do. Ampère showed that two parallel wires carrying current in the same direction attract each other. Two parallel wires carrying current in opposite directions repel each other. This was astonishing. You didn't need a magnet at all. Two ordinary wires carrying ordinary currents exerted forces on each other. Electricity wasn't just connected to magnetism in some vague, indirect way. Electric currents were generating magnetic fields, and those fields were producing real, measurable mechanical forces. Ampère went further, much further. He developed a mathematical framework describing these forces, what we now call Ampère's law. And he proposed something truly radical. He suggested that all magnetism, everywhere, is caused by electric currents. A permanent magnet, like a compass needle or a lodestone, isn't fundamentally different from a current-carrying wire. There must be tiny circular currents flowing inside the iron itself, at a scale too small to see, and those microscopic currents are what create the magnetic effect. He called them molecular currents. Think about how bold that idea is.
Ampère was saying that there's no such thing as magnetism as an independent force. There's only electricity. Magnetism is simply what electricity does when it moves in circles. Every magnet is secretly an electrical device. Every compass needle pointing north is being pushed around by invisible microscopic currents circulating inside the iron. And he was right. It would take another 100 years and the development of quantum mechanics to explain exactly why those currents exist. But the basic insight that magnetism is a manifestation of moving charges was correct. The unit of electric current, the ampere, carries his name. So by 1820, the scientific world knew that electric currents produce magnetic fields. Ørsted had demonstrated it. Ampère had quantified it. The first half of the electricity-magnetism connection was established. But immediately, an obvious question arose. A tantalizing, maddening question.
If electricity can create magnetism, can magnetism create electricity? And here's something worth pausing on, because it reveals the depth of what Ørsted had stumbled upon. The magnetic force around a current-carrying wire doesn't behave like any force that anyone had seen before. Gravity pulls things straight down. The electric force between charges pushes them directly toward or away from each other. These are radial forces, pointing along the line between the objects. But the magnetic force around Ørsted's wire was circular. It curled around the wire in loops. It didn't point toward the wire or away from it. It pointed around it, sideways, tangentially, tracing out invisible circles in the air. This was genuinely weird. Nobody had ever encountered a force that behaved this way. Forces were supposed to act along straight lines between objects. That was how gravity worked. That was how electrical attraction and repulsion worked. That was how everything worked.
And here was a force that acted at right angles to the straight line. A force that spun things around instead of pushing them toward or pulling them away. Ørsted published his results carefully, sending copies of his paper to scientific societies across Europe. And the effect was like dropping a stone into still water. Ripples spread outward in every direction. Within months, laboratories across the continent were buzzing with activity, repeating Ørsted's experiment, extending it, trying to understand what it meant. And the person who moved fastest, who seized the result and wrung more out of it in a shorter time than anyone else, was Ampère, working in Paris. But Ampère wasn't the only one responding to Ørsted's discovery. In London, a man named William Sturgeon took a very practical approach. In 1825, Sturgeon wrapped insulated copper wire around a bar of iron and connected the wire to a battery. When current flowed, the iron bar became a powerful magnet.
When the current stopped, the magnetism disappeared. Sturgeon had built the first electromagnet. A magnet you could turn on and off at will. Think about what that meant for practical applications. A permanent magnet is always on. You can't control it. But an electromagnet is obedient. It does what you tell it. Send current, get magnetism. Stop current, lose magnetism. Reverse the current, reverse the poles. This controllability is the foundation of essentially every electromagnetic machine that followed. Electric motors use electromagnets to create rotating magnetic fields. Telegraphs use electromagnets to move levers. Telephone receivers use electromagnets to vibrate membranes. Hard drives use electromagnets to read and write data. MRI machines use enormously powerful electromagnets to align the nuclear spins of hydrogen atoms in your body. All of it traces back to Sturgeon's copper wire wrapped around an iron bar.
An American named Joseph Henry improved Sturgeon's design dramatically.
Henry discovered that by using insulated wire and winding many layers of coils, he could create electromagnets of staggering power. By 1831, he had built an electromagnet that could lift over a ton of iron. Henry also independently discovered electromagnetic induction at almost the same time as Faraday, and there's an argument to be made that he found it first. But Faraday published first, and in science, publication is what counts. Henry accepted this with remarkable grace and spent the rest of his career doing important work on electromagnetism and eventually becoming the first secretary of the Smithsonian Institution in Washington. The electromagnetic was also the key component in the telegraph, the first practical electromagnetic technology to reach the general public. The basic idea was simple. You run a wire between two locations. At the sending end, you have a switch.
At the receiving end, you have an electromagnet connected to a lever. When you close the switch, current flows through the wire, the electromagnet activates, and the lever moves at the distant end. Open the switch, the current stops, the magnet releases, and the lever returns to its resting position. Short taps of the switch produce short clicks. Long presses produce longer responses. Encode the alphabet into a pattern of short and long signals, dots and dashes, and you have a system for sending written messages at the speed of an electrical signal. Samuel Morse didn't invent the telegraph exactly, but he did develop the most successful version of it, and, crucially, the code that bears his name. By 1844, the first commercial telegraph line was operating between Washington and Baltimore.
By the 1860s, telegraph lines stretched across continents and under oceans, connecting London to New York, Europe to India, the entire world wired together for the first time in human history. Messages that had previously taken weeks or months to deliver by ship could now arrive in minutes. The telegraph was the internet of the 19th century, and it ran on electromagnetism, on the principle that Ørsted had demonstrated in a lecture hall in Copenhagen, that an electric current produces a magnetic field. Wrap some wire around iron, send current from far away, and you can move a lever, ring a bell, make a mark on a paper tape, at any distance, instantly. The invisible connection between electricity and magnetism, discovered almost by accident during a classroom demonstration, had within 2 decades reshaped the way human beings communicated across the surface of the planet. But the biggest question was still hanging in the air, unanswered.
Ørsted had shown that electricity produces magnetism. Could the process be reversed? Could magnetism produce electricity? If current in a wire made a compass needle move, could a moving compass needle make current flow in a wire? This is the question that consumed Michael Faraday. Several people were chasing this problem in the 1820s, but the one who would crack it, and the way he cracked it, is one of the greatest stories in the entire history of science. Because the man who figured out how to turn magnetism into electricity was not a university professor. He was not a trained mathematician. He had almost no formal education beyond basic reading and writing. He had grown up poor, genuinely poor, in a working-class family in South London, and he had spent his teenage years binding books in a shop. His name was Michael Faraday. Faraday was born in 1791 in Newington Butts, now part of South London.
His father was a blacksmith who was frequently too ill to work. The family scraped by. Faraday later recalled weeks when he and his siblings shared a single loaf of bread. At 13, he was apprenticed to a bookbinder named George Ribau. And this turns out to be one of the most consequential accidents in the history of science, because a bookbinder's apprentice is surrounded by books. Faraday read everything that passed through the shop. 2 works in particular changed his life. One was an article on electricity in the Encyclopaedia Britannica. The other was a popular science book called Conversations on Chemistry by Jane Marcet, written specifically to make chemistry accessible to people without formal training. Faraday didn't just read these books, he started doing experiments. He built a crude electrostatic generator out of bottles and scrap wood. He performed chemical experiments in the back of the bookbinding shop. He started attending public lectures at the Royal Institution, one of London's great scientific venues. In 1812, when he was 20, a customer gave him tickets to a series of lectures by Humphrey Davy, who was by then the most famous chemist in England. Faraday attended the lectures, took meticulous, beautifully detailed notes, bound them into a book, because of course he could, and sent them to Davy with a letter asking for a job. Any job. Davy was impressed enough that when a position as laboratory assistant opened up at the Royal Institution in 1813, he hired Faraday. And that was the door. A bookbinder's apprentice walked into one of the finest scientific laboratories in the world, and he never left. Faraday's early years at the institution were spent doing chemistry, and he was brilliant at it. He discovered benzene, he liquefied chlorine, he did important work on steel alloys. But the thing that would make him immortal started in the 1820s, when he turned his attention to the relationship between electricity and magnetism. He was consumed by the question that Ørsted and Ampere's work had raised. Electricity produces magnetism. Can you reverse it? Can magnetism produce electricity? He tried experiment after experiment. He placed a wire near a magnet and connected it to a galvanometer, which is a sensitive instrument for detecting small currents. Nothing. The needle sat still. He wrapped wire around a magnet. Nothing. He tried different configurations, different materials, different strengths of magnet. Year after year, nothing. But here's the thing, and it's what made this so maddeningly difficult. Faraday was looking for a steady current.
He expected that a magnet sitting near a wire would produce a continuous flow of electricity, the same way a wire carrying a continuous current produces a continuous magnetic field.
That seemed like the natural symmetry. If a steady current makes a steady magnetic field, then a steady magnetic field should make a steady current. It doesn't. And that word, doesn't, contains one of the deepest insights in all of electromagnetism. But it took Faraday 10 years to find it. The breakthrough came on August 29, 1831. Faraday had built a device consisting of an iron ring about 6 inches across, with 2 separate coils of wire wound around it on opposite sides. One coil was connected to a battery. The other was connected to a galvanometer. His idea was that if electricity in the first coil created magnetism, and that magnetism traveled through the iron ring to the second coil, maybe it would induce electricity in the second coil. He connected the battery. The galvanometer needle jumped. It twitched, and then it settled back to 0. He stared at it. When he disconnected the battery, the needle jumped again, in the opposite direction, and then settled back to 0. The current in the second coil appeared only at the moment of change. When the battery was connected, the magnetic field through the ring was increasing, and a current flowed. When the field stabilized, even though it was still strong, nothing happened. When the battery was disconnected, the field was decreasing, and a current flowed again, in the reverse direction. Faraday had discovered electromagnetic induction, and the key insight, the one that had eluded everyone, was breathtaking in its simplicity. A magnetic field doesn't produce electricity. A changing magnetic field produces electricity. But here's the thing, the change is everything. A magnet sitting still next to a wire does nothing. Move that magnet, push it into a coil or pull it away, and a current flows. Stop moving it, and the current stops. The signal lives not in the field itself, but in the variation, in the motion, in the transition from one state to another. This is Faraday's law of electromagnetic induction, and it is, without exaggeration, the principle behind every electrical generator ever built. Every power plant on Earth, whether it burns coal, splits atoms, catches the wind, or dams a river, does fundamentally the same thing. It spins a magnet inside a coil of wire. The changing magnetic field pushes electrons through the wire, creating current. The basic mechanism is exactly what Faraday demonstrated in 1831 with his iron ring and his galvanometer. The scale is unimaginably larger. The engineering is vastly more sophisticated, but the principle is identical. Every time you turn on a light, you are using Faraday's discovery. Every time you charge your phone, every time an electric train moves, every time a factory runs, somewhere a magnetic field is changing inside a coil of wire and electrons are being pushed. Faraday gave us that. A man who couldn't do calculus, who had never attended a university, who started out as a bookbinder's apprentice, sharing a loaf of bread with his siblings. But Faraday did something else, something less immediately practical but far more profound. He developed a way of thinking about electric and magnetic forces that would eventually reshape all of physics. He invented the concept of the field. Before Faraday, the standard way of thinking about forces was what physicists call action at a distance. Two charges push or pull on each other across empty space. Two magnets attract or repel through the void. The force just reaches across the gap, instantaneously, with nothing in between. Newton's gravity worked the same way. The sun pulls the earth pulls the sun. And nobody worries too much about how the force gets from one to the other. The space between them is empty, irrelevant. just a gap to be crossed. Faraday found this deeply unsatisfying. When he looked at iron filings arranging themselves around a magnet, forming those beautiful curving patterns that fan out from pole to pole, he didn't see a mathematical abstraction. He saw something real. He saw lines of force filling the space, threading through every point, giving the space itself a kind of structure, a kind of tension. And he believed those lines were physically meaningful. The space around a magnet isn't empty. It's filled with something, a condition, a state, a field. Most of the mathematically trained physicists on the continent thought this was a bit naive. They had their equations, their inverse square laws, their elegant formalisms. They didn't need to imagine invisible lines filling up space. But here's the thing.
Faraday was right. Profoundly, fundamentally right. The concept of the field would become the central idea in all of modern physics. Every force we know about, electromagnetic, gravitational, nuclear, is now understood in terms of fields. Faraday saw it first, and he saw it because he couldn't do the math. His lack of formal mathematical training forced him to think in physical, spatial, intuitive terms, to imagine the space itself doing something rather than just writing down formulas for the forces between distant objects. That's one of the beautiful ironies of this story. The man who gave physics its most important conceptual tool did so precisely because he lacked the conventional tools of his profession. In 1845, Faraday made another discovery that stunned the scientific world. He showed that a strong magnetic field could rotate the plane of polarized light. This effect, now called Faraday rotation, was the first experimental evidence that light and electromagnetism were somehow connected. Light, that most familiar and most mysterious of phenomena, was tangled up with the same forces that made compass needles twitch and iron filings arrange themselves into patterns. Faraday suspected, and wrote about it in his notebooks, that light itself might be a vibration of his lines of force, an electromagnetic disturbance rippling outward through space. He didn't have the mathematics to prove it, but someone else did. Now, to understand what Faraday did, and more importantly how he did it, you need to understand something about the way his mind worked. Because Faraday's approach to physics was unlike anyone else's in his era, and it produced results that the more conventionally trained physicists of his day couldn't have reached. Faraday had almost no mathematical training. He couldn't do calculus.
He couldn't write down the kinds of equations that Ampère wielded so fluently. And in the early 19th century, the most prestigious physics was mathematical physics. If you couldn't express your ideas in the language of differential equations, you were, in the eyes of many continental physicists, not really doing serious science. You were just tinkering. But Faraday had something that compensated for his lack of mathematics, something that turned out to be not just an adequate substitute, but, in this particular case, a genuine advantage. He thought in pictures. He thought in physical images, in spatial relationships, in the way things move and flow and fill space. When he looked at iron filings arranging themselves around a magnet, those beautiful curving patterns that fan out from one pole and sweep around to the other, he didn't see a pretty demonstration to impress lecture audiences. He saw the actual structure of something real. He saw lines of force, filling the space, giving it tension and direction and energy. He believed those lines were not just a visual metaphor, but a physical reality. The space around a magnet wasn't empty. It was full of something, a condition, a strain, a field. This was a radical departure from the way everyone else was thinking about forces. The standard view, which had worked perfectly well for gravity and for electrostatics, was action at a distance. Two objects exert a force on each other, across the gap between them, and nothing in the gap matters. The sun pulls the earth pulls the sun. The force just reaches across empty space, instantaneously, without any intermediary. Newton himself had admitted that he found this idea troubling, that the notion of a force acting through a vacuum without any physical mechanism seemed so great an absurdity that I believe no man who has, in philosophical matters, a competent faculty of thinking can ever fall into it. But he couldn't find an alternative, so he used it anyway. And it worked, and everyone accepted it. Faraday couldn't accept it. When he looked at his lines of force, he saw the mechanism that Newton had been missing. The force doesn't leap across empty space. It fills the space. It spreads through the space, point by point, creating a condition at each location. And that condition is what exerts the force on any charged object or magnet that happens to be there. The field is the thing. The source creates the field, and the field acts on whatever is in it. Remove the source, and the field collapses. But as long as the source is there, the field fills the space around it, carrying energy and exerting force. After the discovery of electromagnetic induction in 1831, Faraday spent the rest of the decade and into the 1840s exploring its implications from every angle. He showed that you could generate a current by pushing a bar magnet into a coil of wire, and that the current reversed when you pulled the magnet back out. He built the first electrical generator, a copper disc spinning between the poles of a magnet, which produced a small but steady current. It was crude, barely functional, generating only enough electricity to barely deflect a galvanometer needle. But the principle was there. Mechanical motion could be converted into electrical current through a changing magnetic field. He also discovered something that seemed, at first, to be just an annoying complication, but turned out to contain a deep physical principle. When he tried to change the current flowing through a coil of wire, the coil resisted the change. If the current was increasing, the coil generated a momentary opposing voltage that fought the increase. If the current was decreasing, the coil generated a voltage that tried to sustain it. The coil behaved as if it had a kind of electrical inertia, a reluctance to let the current change. This effect was formalized by a Russian physicist named Heinrich Hertz, who stated the principle that bears his name. Lenz's law says that any induced current will flow in a direction that opposes the change that caused it. Push a magnet toward a coil, and the induced current creates a magnetic field that pushes back against the magnet. Pull the magnet away, and the induced current creates a field that tries to hold the magnet in place. Nature resists change. The system always fights back against whatever is being done to it. This sounds like a small technical detail, but it has enormous practical consequences. It's the principle behind eddy current brakes, which are used in roller coasters and high-speed trains to slow down without any friction or wear. A conductive metal plate moves through a magnetic field. The changing field induces currents in the plate, and those currents produce their own magnetic field, opposing the motion, slowing the plate down. No contact, no brake pads, just a magnet, a conductor, and the invisible hand of Lenz's law. And Lenz's law is also, at a deeper level, a manifestation of conservation of energy. If an induced current could flow in the same direction as the change causing it, rather than opposing it, the system would accelerate itself. The current would reinforce the change, which would strengthen the current, which would reinforce the change further, in an ever-growing feedback loop that created energy from nothing. That would violate one of the most fundamental principles in all of physics. Lenz's law ensures it can't happen. The opposition is mandatory. Nature always charges a price for the energy you extract from a changing magnetic field. Through the 1830s and 1840s, Faraday kept pushing, kept experimenting, kept developing his picture of invisible lines of force filling all of space. He discovered that different materials responded to magnetic fields in different ways. Some, like iron, were strongly attracted and would concentrate the field lines within themselves. He called these paramagnetic materials. Others, like bismuth, were weakly repelled and would push the field lines outward. He called these diamagnetic. The fact that every material, not just iron, responded to magnetic fields in some way reinforced his conviction that the fields were real physical entities, not just convenient mathematical descriptions. And in 1845, Faraday made a discovery that would connect electromagnetism to something seemingly unrelated and set the stage for the next great unification. He showed that a strong magnetic field could rotate the plane of polarized light.
Polarized light is light in which the electromagnetic waves oscillate in a single plane rather than in random orientations. When Faraday sent polarized light through a piece of heavy glass placed between the poles of a powerful electromagnet, the plane of polarization rotated. The magnetic field was doing something to the light. This was the first concrete experimental evidence that light and magnetism were connected. Not just philosophically or speculatively, but physically, measurably, in a laboratory. Something about the magnetic field was reaching into the beam of light and twisting it. Faraday wrote in his notebook that light might be a vibration of his lines of force, an electromagnetic disturbance propagating through the field. He suspected that light itself was electromagnetic in nature. He didn't have the mathematics to prove it, he knew he didn't. And that knowledge must have been both frustrating and motivating, because Faraday spent the remaining years of his active career trying to push the connection further, to find more links between light and electromagnetism, to build an ever more complete picture of the unified field that he sensed but couldn't quite formalize. The formalization would come from someone else, someone who had all the mathematics Faraday lacked, and who also had the wisdom to take Faraday's physical intuition seriously, at a time when most of the mathematical establishment dismissed it. That someone was working in Edinburgh and Cambridge, reading Faraday's papers with growing excitement, and beginning to suspect that those naive-seeming lines of force contained the key to the deepest unified theory the world had ever seen. He was working in Edinburgh. His name was James Clerk Maxwell.
And what Maxwell was about to do with Faraday's physical intuition would be one of the most breathtaking intellectual achievements in the history of human thought. James Clerk Maxwell was born in Edinburgh in 1831, the same year Faraday discovered electromagnetic induction, which is a coincidence so perfectly timed it almost feels scripted. He grew up in a well-off Scottish family, spent much of his childhood at the family estate in Glenlair, in the countryside of Galloway. And from a very young age, he was the kind of child who drove adults slightly crazy with questions. His mother described him at age 3, constantly asking, "What's the go of that? What does it do?" And if the answer wasn't satisfying enough, he'd follow up with, "But what's the particular go of it?" Which is a pretty good description of the scientific method coming from a toddler. His mother died when he was 8, cancer, and that loss shaped him deeply. He was initially educated by a tutor who was, by most accounts, not very good. But the boy's talent was so obvious that he eventually ended up at the Edinburgh Academy, where at age 14 he published his first mathematical paper on a method for drawing oval curves, which was presented to the Royal Society of Edinburgh. 14 years old, presenting a paper to one of the most prestigious scientific bodies in the world. He went on to the University of Edinburgh and then to Cambridge, where he became a Fellow of Trinity College, one of the most elite academic positions in Britain. And it was during the late 1850s and into the 1860s that Maxwell turned his attention to the problem that Faraday had spent decades wrestling with: the nature of electric and magnetic fields. Here's what Maxwell understood, and this is crucial. By the 1850s, there was an enormous amount of experimental knowledge about electricity and magnetism. Coulomb had measured the force between charges. Ampère had described how currents interact. Faraday had discovered induction. Biot and Savart had quantified the magnetic field around a wire. There were dozens of known relationships, hundreds of experimental results, and a mountain of data that had been collected over the previous century by some of the finest experimenters who ever lived. But there was no unified mathematical framework tying it all together. It was like having 1,000 puzzle pieces scattered on a table with no picture on the box. You could see clusters here and there, groups of 3 or 4 pieces that fit together, but the overall pattern remained invisible. Maxwell decided to build the picture. Maxwell's approach was methodical and patient, and it unfolded over about a decade. His first major paper on the subject, published in 1855, when he was only 24, was called On Faraday's Lines of Force. And the title itself was a statement. He wasn't ashamed to be building on Faraday's intuitive, non-mathematical framework. He was celebrating it. Where other mathematical physicists saw Faraday's lines of force as beneath serious attention, Maxwell saw them as a treasure waiting to be translated. In that first paper, Maxwell used an analogy. He compared Faraday's lines of force to the flow of an imaginary incompressible fluid through tubes of varying width. Where the tubes were narrow, the fluid flowed fast, corresponding to a strong field. Where the tubes were wide, the fluid flowed slowly, corresponding to a weak field. This wasn't meant to be a literal description of what the electromagnetic field actually is. It was a mathematical model, a way to capture Faraday's physical intuition in the precise language of differential equations, without yet committing to a specific physical mechanism. It was clever, it was humble, and it worked. Maxwell was able to reproduce all the known laws of electrostatics and magnetostatics using this fluid analogy, showing that Faraday's field picture was mathematically equivalent to the action at a distance theories that everyone else was using. The results were the same. The picture was different, and Maxwell's picture, Faraday's picture, was more physically satisfying. His second major paper, published in 1861 and 62, was more ambitious and more strange. In it, Maxwell imagined the electromagnetic field as a kind of mechanical system, a medium filled with tiny rotating cells, molecular vortices, separated by layers of small idle wheel particles. The rotating cells produced the magnetic field. The idle wheels between them could transmit the rotation from one cell to the next, and their motion corresponded to electric current. It was a bizarre, almost Victorian steampunk vision of the invisible world, and Maxwell himself didn't fully believe in its literal reality. But it served its purpose, which was to give him a mathematical framework for writing down equations that described how electric and magnetic fields interact with each other. And then, in a paper published in 1865, and in a later, more complete treatment in his 1873 Treatise on Electricity and Magnetism, Maxwell presented the final form of his theory. 4 equations, just 4, written in the compact notation of vector calculus. And those 4 equations described everything that was known about electricity and magnetism. Every experimental result, every observed phenomenon, every relationship that anyone had ever discovered, was contained in those 4 lines of mathematics. Let me walk you through what each one says. Not in the language of math, because this is a story, not a textbook, but in the language of what they mean. The first equation says that electric charges create electric fields. Specifically, it says that the electric field radiates outward from a positive charge and inward toward a negative charge, spreading out into space the way light from a lamp spreads into a dark room. The total field emanating from a region of space is proportional to the total charge enclosed within that region. This is Gauss's law for electricity, named after the great German mathematician Carl Friedrich Gauss, who formulated the mathematical principle that Maxwell incorporated. The second equation says something about magnetic fields that is, in a way, even more interesting than the first, precisely because of what it denies. It says that there are no magnetic charges, no magnetic monopoles.
You can have a positive electric charge and a negative electric charge sitting separately, on their own. But you can never have a north magnetic pole without an accompanying south magnetic pole. Cut a magnet in half and you get two smaller magnets, each with its own north and south pole. Try again. Cut those in half. Same result. You can never isolate a magnetic pole. The magnetic field lines always form closed loops. They come out of the North Pole, curve through space, and loop back into the South Pole, continuing through the interior of the magnet back to the North Pole again. No beginning, no end. Just endless loops. This is Gauss's law for magnetism. And the fact that magnetic monopoles don't seem to exist is one of the deep asymmetries in physics. Paul Dirac showed in 1931 that if even a single magnetic monopole existed anywhere in the universe, it would explain why electric charge comes in discrete units rather than continuous amounts.
Physicists have been searching for magnetic monopoles ever since. They've looked in cosmic rays, in particle accelerators, in moon rocks. Nobody has ever found one. As of right now, the universe appears to have electric charges without magnetic charges. The second equation stands. The symmetry between electricity and magnetism is imperfect. And that imperfection, as we'll see, matters. The third equation is Faraday's law, expressed mathematically. It says that a changing magnetic field creates an electric field. Specifically, if the magnetic field through a loop of wire is increasing or decreasing, an electric field appears along that loop, and that electric field pushes charges around, creating a current. This is the principle behind every generator on Earth, every transformer in every electrical substation, every induction cooktop in every modern kitchen. Change the magnetic field and an electric field springs into existence. And then the fourth equation.
This is the one where Maxwell showed his genius most clearly, because the fourth equation contains something that no experimentalist had ever directly observed. Something Maxwell added purely from mathematical reasoning and physical intuition. Something that turned out to be the key to the entire structure, the piece that nobody else could see. The fourth equation starts with Ampere's law, the well-established fact that electric currents create magnetic fields. A wire carrying current produces a magnetic field circling around it. Ampere had established this back in 1820, and it was solid, well-confirmed physics. And it was within this mechanical model that Maxwell made his most important discovery. He found the displacement current. I want to say something about the sheer courage of Maxwell's displacement current, because I don't think its audacity is always appreciated. Every other term in Maxwell's four equations had experimental backing. Coulomb had measured the electric force. Ampère had measured the magnetic force between wires. Faraday had demonstrated induction. These were observed facts, translated into mathematics. But the displacement current was different. But here's the thing, nobody had observed it. Nobody had measured it. Nobody had designed an experiment to test it. Maxwell added it because the mathematics required it. Because without it, the equations were internally inconsistent. Because a gap needed filling, and only one piece could fill it. That is an extraordinary thing to do. Most scientists, even very good ones, are reluctant to add terms to equations that haven't been experimentally verified. The whole point of physics is to describe what we observe, and adding unobserved terms to your equations feels dangerously close to making things up. But Maxwell trusted the mathematics. He trusted the pattern.
He believed that if the equations demanded a displacement current, then nature must provide one, even if nobody had seen it yet. And he was right. The displacement current is real. It's measurable. It produces exactly the magnetic fields that Maxwell predicted. And without it, there would be no electromagnetic waves, no light as an electromagnetic phenomenon, no radio, no television, no wireless communication, no modern world as we know it. The entire edifice of electromagnetic wave theory and everything that flows from it rests on a term that one man added to one equation because the math told him it had to be there. There is a lesson in that. Sometimes the pattern is smarter than the pattern finder. Sometimes the mathematics knows something about the world that the experimenter hasn't discovered yet. And the willingness to trust the pattern, to follow the logic, even when it leads somewhere unfamiliar, is one of the rarest and most valuable qualities a scientist can have.
Einstein had it. Dirac had it. Maxwell had it first. And the displacement current is perhaps the purest example in all of physics of mathematical reasoning leading to physical discovery. Let me explain what the displacement current is and why it matters, because this is the crux of the whole story, the hinge on which the next unification turns. Ampere's law, as originally stated, says that electric currents create magnetic fields. Specifically, if you draw an imaginary circle around a wire carrying current, the magnetic field circling along that loop is proportional to the current passing through any surface bounded by the loop. This works perfectly in situations where currents flow continuously through complete circuits. But what about a capacitor? A capacitor is two metal plates separated by a gap, maybe just air, maybe a sheet of glass or plastic. When you connect a capacitor to a battery, current flows into one plate and out of the other. Charge builds up on the plates. But no actual current crosses the gap. The electrons pile up on one plate and drain off the other, but none of them jump across. There is a physical gap in the circuit where no charges are moving, and here's the problem. If you draw an imaginary loop around the wire leading to the capacitor and stretch a flat surface across that loop, the surface intersects the wire, and you can count the current passing through it. Ampere's law works fine, but now stretch a different surface across the same loop, a bulging surface that curves down and passes through the gap between the capacitor plates where no current flows. Ampere's law says the magnetic field around the loop should depend on the current passing through this surface. But there is no current passing through this surface. The two surfaces are bounded by the same loop, so they should give the same answer. But one says there's current and the other says there isn't. The equations are contradicting themselves. Something is missing.
Maxwell realized that while no actual charge is crossing the gap, the electric field between the plates is changing. As charge builds up on the plates, the electric field in the gap grows stronger. And Maxwell proposed that this changing electric field is equivalent in terms of its ability to produce a magnetic field to an actual current. He called it the displacement current, and he added it to Ampere's law, creating the fourth and final equation of his system. This might sound like a minor technical patch. It isn't. It's the linchpin of the entire theory of electromagnetic waves. Because before Maxwell added the displacement current, the equations described a world in which electric currents create magnetic fields, and changing magnetic fields create electric fields. But the chain stops there. The changing electric field doesn't do anything further. The loop is broken. With the displacement current, the loop closes.
A changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. Each feeds the other. And a disturbance in one can propagate outward through space, self-sustaining, as the electric part creates the magnetic part, and the magnetic part creates the electric part, alternating, leapfrogging, racing forward at a speed determined by the fundamental constants of electricity and magnetism. Maxwell derived the speed of this disturbance. He combined the permittivity of free space, a number from electrostatics that Coulomb had effectively measured, with the permeability of free space, a number from magnetostatics that Ampère had effectively measured, and plugged them into the wave equation that emerged from his 4 completed equations. And the answer came out to be roughly 193,000 miles per second. The speed of light had been measured at roughly 186,000 miles per second. The agreement was too close to be a coincidence. Maxwell didn't stumble onto this. He calculated it carefully, checked it, and then sat with the implications. 2 numbers from the world of sparks and magnets, numbers that had been measured in laboratories using charges and wires, and nothing to do with light or optics, combined to give the speed of a wave that traveled at the speed of light. The conclusion was inescapable, and Maxwell knew it. He wrote to a colleague that the agreement between the calculated speed and the measured speed of light was so striking that light must be an electromagnetic wave. Let me try to convey why this was so profound, because I think the magnitude of it can get lost in the retelling. Before Maxwell, physics had 3 separate departments, 3 separate communities, 3 separate sets of textbooks: electricity, magnetism, optics. These were different subjects, studied by different people, with different techniques, different apparatus, different journals. An expert in optics might never touch a battery. An expert in electricity might never think about lenses. They were neighboring buildings on a university campus, each with its own faculty, its own traditions, its own culture. And Maxwell showed that all 3 buildings were rooms in the same house, that the light an optician studied through prisms and lenses was made of the same stuff as the field an electrician measured with a galvanometer, that the rainbow and the compass needle were manifestations of one entity, and not just visible light. Maxwell's equations put no constraint on the frequency of electromagnetic waves. Any frequency should work. A wave oscillating a few 100 trillion times per second is visible light. But what about a wave oscillating 1,000,000 times per second, or 1,000,000,000, or a quintillion? The equations said those waves should exist too, traveling at the same speed, obeying the same laws, differing only in their wavelength and frequency. Maxwell had predicted the existence of an entire invisible spectrum of radiation, stretching from the longest, laziest radio waves to the most energetic, most penetrating gamma rays, most of which no one had ever detected. Radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays, all of them predicted by 4 equations and a displacement current. All of them confirmed over the following decades and centuries. All of them electromagnetic. Maxwell died in 1879. He was 48 years old. He never saw his waves experimental long, but he left behind the 4 most important equations in the history of physics, and a unified theory so powerful that when Albert Einstein was asked if he stood on Newton's shoulders, Einstein reportedly answered that he stood on the shoulders of Maxwell. The experimental confirmation came 9 years after Maxwell's death, in 1887, from Heinrich Hertz. Hertz was a German physicist, trained in Berlin under Hermann von Helmholtz, who was one of the grand old men of German physics. Helmholtz had been encouraging his students to test Maxwell's predictions, and Hertz, a gifted experimentalist, took up the challenge with characteristic thoroughness. His apparatus was elegant in its simplicity. The transmitter was a pair of metal rods with a small gap between them, connected to a circuit that produced rapid electrical oscillations. When the voltage across the gap was high enough, a spark jumped, and that sudden burst of current should, according to Maxwell, launch an electromagnetic wave into the room. The receiver was even simpler, just a loop of wire with a tiny gap. If a wave passed through the loop, it would induce a current, and if the current was strong enough, a minuscule spark would jump across the gap. Hertz spent months in a darkened room, peering through a magnifying glass at the tiny gap in his receiver, looking for the faintest glimmer. And he found it. A barely visible spark, but real and reproducible. Electromagnetic waves were crossing the room, from transmitter to receiver, traveling through empty space at the speed of light. Hertz went on to demonstrate that his waves behaved exactly like light. They could be reflected by metal sheets, like light reflecting off a mirror. They could be refracted, bending as they passed through a prism made of pitch. They could interfere with each other, forming patterns of constructive and destructive interference, standing waves, nodes and antinodes, just as Thomas Young had shown for light with his double-slit experiment. Every property of light that had been catalogued by opticians over the centuries, Hertz could reproduce with his sparks and wires and loops. The only difference was scale. Light waves are tiny, measured in millionths of an inch. Hertz's waves were measured in meters. But they were the same thing. The same equations described them. The same speed characterized them. The same field produced them. But here's the thing about Hertz. When a journalist asked him about the practical implications of his discovery, Hertz replied that he saw none. "It's of no use whatsoever," he said. "This is just an experiment that proves Maestro Maxwell was right. We just have these mysterious electromagnetic waves that we cannot see with the naked eye. But they are there." Within 20 years, Marconi was sending radio signals across the Atlantic. Within 50, radar was tracking aircraft. Within a century, the entire planet was bathed in a continuous ocean of electromagnetic waves, carrying voice, image, data, every kind of signal imaginable, through the air that Hertz had once peered into with a magnifying glass, looking for a barely visible spark. Hertz died young, at 36, of a rare disease that attacked his blood vessels. He never saw the revolution his work unleashed. But the unit of frequency, cycles per second, carries his name. Every time you see hertz, megahertz, gigahertz on a specification sheet, a radio dial, or the clock speed of your computer, that's him. By the end of the 19th century, the unification was breathtaking. Electricity, magnetism, and light were one. The amber effect that Thales had marveled at, the lodestone that guided sailors, the candle flame that lit dinner tables, the rainbow that arched across the sky after a storm. These were all aspects of a single force, described by 4 equations, mediated by a single field. 3 drawers, opened and revealed to contain the same thing. And yet, something about the theory was unsatisfying. Maxwell's equations described E and B, electric fields and magnetic fields, as 2 intertwined but distinct entities. 2 fields, not 1.
They influenced each other. They danced together. They couldn't exist in isolation in a traveling wave. But they remained, mathematically, 2 separate objects. 2 vectors at every point in space, 2 columns in the ledger. And there was that curious asymmetry, the one about the magnet and the wire, that seemed to suggest the distinction between E and B was not as fundamental as the equations implied. That maybe the split was an artifact, a consequence of how we, as stationary 3-dimensional observers, carve up a 4-dimensional reality that doesn't actually split that way. That asymmetry gnawed at a young clerk working in a patent office in Bern, Switzerland, who had been thinking about light and motion and the strange relationship between electric and magnetic fields since he was a teenager. His name was Albert Einstein, and the paper he published in 1905 would tear down another wall, revealing that electricity and magnetism aren't really two separate fields at all. Here's something that often gets lost in the popular telling of Einstein's story. When people talk about special relativity, they usually start with trains and clocks and twins aging at different rates, and it all sounds very abstract, very removed from everyday experience. But the paper that started it all, the one Einstein published in June of 1905, doesn't begin with trains. It doesn't begin with thought experiments about riding alongside a beam of light, although Einstein had been mulling that over since he was 16. But here's the thing. It begins with exactly the problem I just described: a magnet and a conductor. The very first paragraph of On the Electrodynamics of Moving Bodies, which is the actual title of the paper that introduced special relativity to the world, talks about the asymmetry in Maxwell's theory. Einstein writes about how the observable phenomenon, the current induced in the wire, is the same regardless of whether the magnet moves or the wire moves. But Maxwell's equations give two fundamentally different explanations depending on which one you call stationary. And Einstein says, essentially, this can't be right. If the physics is the same, the explanation should be the same. That conviction, that the laws of physics should look identical to all observers moving at constant velocity relative to each other, became the first postulate of special relativity. The second postulate, equally radical, was that the speed of light in a vacuum is the same for all observers, regardless of their motion. From those two simple statements, everything else follows. Time dilation, length contraction, the relativity of simultaneity, E equals mc squared, all of it flows from two premises that Einstein chose partly because of his dissatisfaction with the way Maxwell's equations treated the distinction between a moving magnet and a moving wire. And when you work out the full implications of special relativity for electromagnetism, something beautiful happens. The two separate fields, E and B, electric and magnetic, merge into a single mathematical object. In the four-dimensional space-time that special relativity reveals, where time is treated as a fourth dimension alongside the three dimensions of space, the electric field and the magnetic field are not independent entities. They are components of a single thing, a single unified structure called the electromagnetic field tensor. Now, tensor is a mathematical term that might sound intimidating, but the physical idea it captures is something you can actually visualize. Think of it this way. Imagine you're standing on a street corner, watching a parade go by. You see floats moving past you from left to right. A friend of yours is standing on one of the floats, looking out at you. From your perspective, the float is moving. From your friend's perspective, you and the buildings are moving. You're both describing the same physical reality, the same collection of objects in space. But because you're in different states of motion, you carve up that reality differently. What you call moving and stationary depends on your frame of reference. Something very similar happens with electric and magnetic fields. An observer standing still next to a wire carrying current sees a magnetic field circling the wire and no electric field. Because the wire is electrically neutral, it has equal numbers of positive and negative charges. But an observer moving alongside the current, drifting along with the electrons, sees something different. In that observer's frame of reference, the spacing between the positive charges and the spacing between the negative charges is slightly different because of the Lorentz contraction, a consequence of special relativity where moving objects are measured to be slightly shorter along the direction of motion. And slightly different spacing between positive and negative charges means the wire is no longer electrically neutral. One set of charges is slightly more densely packed than the other.
The moving observer sees a net electric charge on the wire, and therefore feels an electric force, not a magnetic one. Same wire, same physical situation. But what one observer experiences as a magnetic force, the other observer experiences as an electric force. The magnetic field and the electric field are not two different things. They are two different perspectives on the same thing. Like two different shadows cast by the same three-dimensional object onto two different walls.
The object is the electromagnetic field, which lives in four-dimensional space-time. The shadows are the electric and magnetic components, which depend on how you're moving through that space-time. This is the fourth unification. And it is, in many ways, the deepest one so far. Because it doesn't just say that electricity and magnetism are connected, the way Ørsted and Faraday showed. It says that the distinction between them is observer-dependent. What counts as electric and what counts as magnetic is not a property of the field itself. It's a property of your motion relative to the field. There is, at the fundamental level, only one field, one entity, one thing. And we experience it as two different forces only because we live in a three-dimensional slice of a four-dimensional reality. Einstein published this in 1905.
3 years later, his former mathematics professor, Hermann Minkowski, gave a famous lecture in which he developed the full mathematical framework for space-time and showed how Maxwell's equations could be written in a breathtakingly compact form using the language of four-dimensional geometry. Minkowski opened the lecture with a line that has become one of the most quoted passages in physics. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. The same could be said of electricity and magnetism. After Einstein and Minkowski, they are doomed to fade away as separate entities. Only the electromagnetic field, the union of the two, preserves an independent reality. Now, let me try to make this a little more concrete, because there's a version of this insight, a way of seeing it, that comes from the physicist Edward Purcell, who wrote one of the most beautiful textbooks on electromagnetism ever published. And Purcell's way of thinking about it is so elegant, so clean, that once you see it, you can never quite unsee it. Imagine a long, straight wire carrying a steady current. Inside that wire, you have two kinds of charged particles. You have the positive ions, which are the metal atoms that have lost an electron, and they're locked in place in the crystal structure of the metal, not moving. And you have the free electrons, which are the ones carrying the current, drifting slowly along the wire, maybe a millimeter per second. Now, from the outside, this wire is electrically neutral. The number of positive charges per unit length is exactly equal to the number of negative charges per unit length.
The positive and negative charges cancel out perfectly. So an electron sitting outside the wire, at rest, feels no electric force. Zero. The wire is neutral. But what if that external electron starts moving, drifting along at the same speed as the electrons inside the wire? In that frame of reference, the electrons inside the wire are standing still, and the positive ions are moving backward. And here's where special relativity enters. Moving objects undergo Lorentz contraction. They're measured to be slightly shorter along the direction of motion. So the positive ions, which are now the ones moving in this frame, are squeezed slightly closer together. Their density goes up by a tiny, tiny amount. Meanwhile, the electrons inside the wire, which are now stationary in this frame, are at their normal spacing. And that means the wire is no longer neutral. In this moving frame, there are slightly more positive charges per unit length than negative charges. The wire has a net positive charge,
and that net positive charge exerts an electric force on the external electron, pulling it toward the wire. That electric force, experienced in the moving frame, is the exact same force that, in the original stationary frame, we call the magnetic force. It's not a different force acting through a different mechanism. It's the same force, Coulomb's electric force, operating on a charge distribution that has been slightly rearranged by the effects of special relativity. The numbers work out perfectly. When you calculate the electric force in the moving frame using Coulomb's law and the Lorentz contracted charge densities, you get exactly the same answer as when you calculate the magnetic force in the stationary frame using the Biot-Savart law. Exactly the same. To every decimal place. Magnetism, in this view, is not a separate force at all. It is a relativistic correction to the electric force.
It arises because of the way Lorentz contraction distorts charge distributions when you change reference frames. If the universe had no special relativity, if there were no speed limit, no Lorentz contraction, there would be no magnetism. Magnets wouldn't work, compasses wouldn't point north, electric motors wouldn't spin. All of magnetism, every refrigerator magnet, every MRI machine, every generator, every electromagnetic wave is a consequence of the fact that the speed of light is finite and the same for all observers. Think about that for a moment. The electrons drifting through a wire in your wall are moving at about 1 millimeter per second. That's roughly 1/1,000,000th the speed of light. The relativistic effects at that speed are unimaginably tiny. The Lorentz contraction of the positive ion spacing is negligible in any normal sense.
But there are so many charges in a wire, trillions upon trillions per inch, that even 1/1,000,000th of a percent change in spacing produces a measurable force. The magnetic force you feel when you hold two magnets near each other, that seemingly robust everyday force, is resting on a foundation of relativistic corrections so small they're barely there. The entire edifice of magnetic technology, every motor, every generator, every transformer, every compass, is built on this whisper-thin sliver of relativity. I find that genuinely breathtaking. The fridge magnet holding up your grocery list is a relativistic phenomenon. The compass needle that guided sailors across oceans for centuries was being pushed around by Lorentz contraction.
The aurora borealis, those shimmering curtains of light in the polar sky, are produced by charged particles from the sun spiraling along Earth's magnetic field lines, which are themselves a manifestation of relativistic effects in the swirling currents of molten iron in Earth's core. It's one thing, seen from different angles, all the way down. And once Einstein and Minkowski showed that E and B are really one field, once special relativity dissolved the boundary between them, a natural question arose. A question that pushed physics into territories that were genuinely new, territories that nobody in the 19th century could have imagined. If the electromagnetic force can be unified with the principles of space-time, if one apparent force, magnetism, turned out to be just another face of electricity when you account for relative motion, then how far does this go? Are there other forces in nature that seem separate but are really one? Is there a deeper unity still, a larger pattern waiting to be uncovered? By the early 20th century, physicists had identified 4 fundamental forces. Gravity, which holds planets in their orbits and keeps your feet on the ground. The electromagnetic force, which holds atoms together, carries light, and does almost everything else you interact with daily. And 2 new forces that had been discovered in the exploration of the atomic nucleus. The strong nuclear force, which binds protons and neutrons together inside the nucleus, overcoming the electromagnetic repulsion between the positively charged protons. And the weak nuclear force, which governs certain kinds of radioactive decay, the process by which unstable atomic nuclei transform into more stable ones, emitting particles in the process. 4 forces, 4 separate, apparently unrelated interactions. And physicists, inspired by Maxwell's unification of electricity, magnetism and light, and by Einstein's unification of E and B into a single space-time field, began to wonder whether these four forces might also be different faces of the same underlying thing. The next wall to fall would be the one between electromagnetism and the weak nuclear force. And the story of how it fell is the story of the fifth and final unification we're going to talk about tonight. Let me take a moment here, because I think this particular unification, the dissolution of the boundary between electric and magnetic fields, deserves a little more space. It's the one that is, in some ways, the most philosophically startling. The earlier unifications showed that phenomena were connected. Lightning is the same as static electricity. Electricity creates magnetism. Light is an electromagnetic wave. These are discoveries about what exists in the world.
But the Einstein-Minkowski unification says something different. It says that the distinction between electric and magnetic fields is not a feature of reality. It is a feature of the observer. That's a much stronger claim. It's not just that E and B are connected, it's that the line between them doesn't exist in nature. We draw it. We impose it on the physics because of the way our bodies move through space-time, because of our particular velocity, our particular reference frame. An observer in a different state of motion draws the line in a different place, and neither observer's line is more real than the other. Consider what this means for a simple bar magnet. You hold it in your hand. In your reference frame, the magnet produces a magnetic field, no electric field. The field lines curve out from the North Pole, loop through space, and return to the South Pole. Pure magnetism in your frame. But for an observer flying past you at high speed, the magnet is moving.
And a moving magnetic field, according to the transformation rules of special relativity, generates an electric field. That observer sees both an electric and a magnetic field surrounding the magnet. Different mixtures of E and B, depending on how fast they're going relative to you. Neither observer is wrong. There is no real answer to the question, is the field around this magnet electric or magnetic? The question itself is incomplete. It's like asking, is the wind blowing from the north or the south, without specifying where you're standing. The answer depends on the observer. The field is the field. It doesn't care about your coordinates. It just exists. And the way you decompose it into electric and magnetic components is a matter of perspective. This is what Minkowski meant when he said that space by itself and time by itself are doomed to fade away. The same logic applies to E and B. Electric field by itself and magnetic field by itself are doomed to fade away.
Only the electromagnetic field, the unified entity that lives in four-dimensional space-time, preserves an independent reality. Now, I want to pause for a moment and make sure something hasn't gotten lost in the sweep of the narrative, because there's a thread running through this entire story that deserves to be pulled out and examined on its own. And that thread is the role of symmetry. Every unification we've discussed tonight was, at its core, the discovery of a symmetry. A symmetry is, loosely, a transformation you can make that leaves the underlying physics unchanged. And the history of electricity and magnetism turns out to be a history of finding deeper and deeper symmetries that connect seemingly different phenomena. Franklin's unification of static and current electricity was, in essence, the recognition that the same substance underlies both.
The symmetry is simple. The laws of electricity don't care whether charge accumulates and discharges in a burst or flows steadily through a wire. The physics is the same. The rules are the same. The phenomena look different because the conditions are different, but the underlying symmetry is perfect. Ørsted and Faraday's discovery that electricity creates magnetism and magnetism creates electricity revealed a deeper symmetry, a kind of reciprocity between the two forces. If you do X with electricity, you get a magnetic effect. If you do X with magnetism, you get an electrical effect. The symmetry isn't perfect, as we discussed, because a steady current creates a steady magnetic field. But a steady magnetic field does not create a steady current. You need change. But the basic reciprocity is there, and it was this reciprocity that Maxwell encoded in his equations. Maxwell's unification of electromagnetism and light revealed a symmetry of the equations themselves. The wave equation that fell out of Maxwell's 4 equations treats electric and magnetic fields on almost equal footing. In a traveling wave, the energy is split evenly between the electric and magnetic components. Each creates the other. Each sustains the other. The symmetry is built into the structure of the wave. Einstein's unification of E and B into a single space-time field revealed a symmetry under Lorentz transformations, the coordinate changes that relate different inertial reference frames. The electromagnetic field is the same for all observers. The way it splits into E and B components changes, but the underlying entity, the field tensor, is invariant. The symmetry is the symmetry of space-time itself, and the electroweak unification reveals a gauge symmetry, a mathematical symmetry of the equations governing the electromagnetic and weak forces. This symmetry says that you can perform certain abstract transformations on the fields, rotations in an internal mathematical space, and the physics doesn't change. The symmetry is hidden at low energies by the Higgs field, which breaks it, giving mass to some of the carrier particles while leaving others massless. But at high enough energies, the symmetry is restored, and the electromagnetic and weak forces become indistinguishable. Each unification uncovered a symmetry that was deeper and more abstract than the last. From the simple symmetry of conservation of charge to the exotic gauge symmetries of quantum field theory. And at each level, the symmetry wasn't just an aesthetic nicety. It was the engine of unification. It was the mathematical structure that forced the apparently different forces to merge. There is a theorem in physics, proved by Emmy Noether in 1918, that connects symmetries to conservation laws. Every continuous symmetry of the laws of physics corresponds to a conserved quantity, something that doesn't change as the system evolves. The symmetry of the laws under shifts in time gives conservation of energy. The symmetry under shifts in space gives conservation of momentum. The symmetry under rotations gives conservation of angular momentum. And the gauge symmetry of electromagnetism gives conservation of electric charge, the very principle that Franklin intuited in the 1740s. Noether was one of the most brilliant mathematicians of the 20th century, and her theorem is one of the deepest results in all of physics. It says that the conservation laws we observe, the quantities that stay constant, the things we can count on, are not arbitrary rules imposed on the universe. They are consequences of symmetries. And that means every unification, every new symmetry discovered, brings with it a new conserved quantity, a new thing you can rely on, a new piece of cosmic bookkeeping that the universe maintains automatically and without error. Symmetry, conservation, unification. These are not 3 separate ideas. They are 3 faces of the same idea. And the history of electricity and magnetism is the clearest, most beautiful illustration of that triple identity in all of science. But before we get to the electroweak unification, we need to talk about what happened to electromagnetism itself when it collided with the other great revolution of the 20th century, quantum mechanics. because the marriage of Maxwell's electromagnetic theory with the strange probabilistic rules of quantum physics produced something called quantum electrodynamics, or QED. And QED is, by some measures, the most successful scientific theory ever created by human beings. Here's the problem that needed solving. Maxwell's theory described electromagnetic fields as smooth, continuous entities, waves that ripple through space, rising and falling like ocean swells. And that picture works beautifully for most purposes. Radio transmitters, power generators, everything we talked about earlier, all of that is perfectly well described by Maxwell's classical electromagnetic theory. But at very small scales, at the level of individual atoms and photons, the smooth, continuous picture breaks down. The first hint came in 1900 from Max Planck, who discovered that the energy of electromagnetic radiation comes in discrete packets, little chunks, which he called quanta. Planck didn't want to believe his own result. He called it an act of desperation, a mathematical trick he used to solve a specific problem about the way hot objects radiate heat. He fully expected that someone would eventually find a way to explain it without quanta. Nobody ever did. Let me say a word about why Planck's discovery was so unsettling, because this matters for the later development of quantum electrodynamics. Before Planck, the electromagnetic field was understood as a perfectly smooth, continuous thing. Maxwell's equations described it as waves, smooth undulations of electric and magnetic fields, spreading through space like ripples on a perfectly calm pond. There were no gaps, no jumps, no discrete steps. The field varied smoothly from one value to the next, at every point, at every moment. And then Planck showed that when electromagnetic radiation interacts with matter, the energy it carries comes in lumps, discrete, indivisible lumps. The energy of each lump is proportional to the frequency of the radiation, a relationship captured in what is now one of the most famous equations in all of physics. E equals h times f, where h is Planck's constant, a number so small that its effects are invisible at everyday scales, but dominant in the atomic world.
The higher the frequency, the bigger the lump. Red light comes in small lumps. Blue light comes in bigger lumps. Gamma rays come in enormous lumps. And you can't have half a lump. The energy is either there in full, or it isn't there at all. This granularity, this pixelation of energy, was completely incompatible with the smooth, continuous picture of the electromagnetic field that Maxwell had so beautifully constructed. Something had to give. Either the field wasn't really continuous, or the interaction between the field and matter introduced the discreteness. As it turned out, the answer was more radical than either option. The field itself is quantized. It comes in packets, and those packets are photons. 5 years later, in 1905, the same year he published the special relativity paper, Einstein took Planck's idea much further. He proposed that light itself is quantized, not just the way light interacts with matter, but light itself. A beam of light, Einstein argued, is not a continuous wave. It is a stream of individual particles, each carrying a specific amount of energy determined by the frequency of the light. These particles would eventually be called photons. This was deeply unsettling to most physicists, because by 1905, the wave nature of light had been thoroughly established. Thomas Young's double-slit experiment in 1801 had demonstrated light interference, a phenomenon that only waves can produce. Maxwell's equations described light as a wave. The wave theory worked. And now Einstein was saying light was also particles, both at the same time.
This was the beginning of wave-particle duality, one of the central mysteries of quantum mechanics, and it applied not just to light, but to all fundamental entities in physics. Over the next 3 decades, physicists struggled to reconcile Maxwell's electromagnetic theory with the new quantum mechanics that was developing in the work of Bohr, Heisenberg, Schrödinger, Dirac, and others. The challenge was formidable. Maxwell's equations were written in the language of classical physics, describing smooth, deterministic fields evolving according to precise mathematical rules. Quantum mechanics was written in a completely different language, a language of probabilities and wave functions and operators and states. Merging these two frameworks required reinventing electromagnetism from the ground up. The person who made the crucial first step was Paul Dirac, an English physicist who was as quiet personally as he was brilliant scientifically. In 1927, Dirac published a paper that is generally considered the birth of quantum electrodynamics. He showed how to quantize the electromagnetic field, to describe it not as a smooth, continuous entity, but as a collection of discrete excitations, each excitation being a photon. In Dirac's framework, the electromagnetic field is like a vast ocean, and photons are the individual waves on its surface. The field is the underlying reality. The photons are the quantized ripples of that reality. But Dirac's early version of QED had a serious problem. When physicists tried to use it to calculate the properties of real particles, properties like the precise magnetic moment of the electron, or the tiny shifts in the energy levels of hydrogen atoms, the equations kept producing infinities. Infinite energies, infinite probabilities, infinite nonsense. The calculations would start out reasonably, and then, at some point, some integral would blow up, diverging to infinity, and the whole answer would become meaningless. For nearly 2 decades, from the late 1920s through the end of the Second World War, this problem of infinities plagued quantum electrodynamics and threatened to derail the entire project. Many physicists, including Dirac himself, suspected that the theory was fundamentally broken, that some entirely new framework would be needed to describe the quantum behavior of electromagnetic fields. And then, in the late 1940s, 3 physicists working independently developed a technique for taming the infinities. Their names were Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga. The technique, called renormalization, is mathematically subtle and conceptually slippery. But the basic idea is that the infinite quantities that appear in the calculations can be absorbed into the measured values of physical constants, the mass and charge of the electron, in a way that is self-consistent and yields finite, meaningful predictions. Feynman also invented an astonishingly intuitive visual language for doing QED calculations. His Feynman diagrams, simple drawings showing particles as lines and their interactions as vertices where lines meet, became the standard tool for every calculation in quantum field theory. Instead of grinding through pages of algebra, physicists could draw a picture and read off the mathematical expression directly. It was a visualization tool for the invisible quantum world, and in a beautiful echo of history, it served the same role for quantum electromagnetism that Faraday's lines of force had served for classical electromagnetism a century earlier, an image that made the invisible comprehensible. Feynman, Schwinger, and Tomonaga shared the Nobel Prize in Physics in 1965 for their work on QED. And the theory they built turned out to be staggeringly accurate. The magnetic moment of the electron, a quantity that measures how strongly the electron interacts with a magnetic field, has been calculated using QED to 12 decimal places and measured experimentally to the same precision. The agreement is perfect, 12 digits.
It's like predicting the distance between New York and Los Angeles to within the thickness of a human hair. No other theory in the history of science has been tested to this level of precision and survived. QED is not just good. It is, in a quantifiable, measurable sense, the most accurate physical theory human beings have ever produced. And at its heart, it is simply the quantum version of Maxwell's electromagnetism. The same field, the same force, the same equations, translated into the language of quantum mechanics and purged of their infinities. But QED did something else, something that would open the door to the next unification. It showed physicists a template, a pattern.
A recipe for building quantum field theories of other forces. If the electromagnetic force could be described as a quantum field, with photons as the quantized carriers of the force, then maybe the other fundamental forces could be described the same way. Maybe the weak nuclear force and the strong nuclear force also had their own quantum fields and their own carrier particles. And the weak force, in particular, had some intriguing similarities with electromagnetism. Both were forces that acted on individual particles. Both could be described in terms of symmetry principles from abstract mathematics, and both seemed to follow patterns that suggested they might be related, like two dialects of the same language. The first person to see the connection clearly was Sheldon Glashow. He was an American physicist, born in New York in 1932, who had studied under Julian Schwinger at Harvard. In 1961, Glashow published a paper proposing a mathematical framework that combined the electromagnetic force and the weak nuclear force into a single, unified description. In this framework, electromagnetism and the weak force were not separate forces that happened to coexist. They were two aspects of a single, more fundamental force, which would eventually be called the electroweak force. But Glashow's theory had a problem, a big one. In his mathematical framework, the carrier particles of the unified electroweak force were all predicted to be massless, like the photon. But the carrier particles of the weak force, which would eventually be observed and named the W and Z bosons, were known to be extremely heavy, thousands of times heavier than a proton. A massless carrier particle produces a force that reaches across infinite distances, like electromagnetism. A massive carrier particle produces a force that drops off sharply with distance, which is exactly what the weak force does. It operates only at subatomic scales, over distances smaller than the nucleus of an atom. So the prediction of massless carriers was clearly wrong. The photon is massless, and that's fine. Electromagnetism reaches across the universe. But the W and Z bosons must be massive, or the weak force would reach across the universe too, which it plainly doesn't. Glashow's framework was mathematically beautiful, but physically broken. The symmetry between electromagnetism and the weak force was there in the equations, but something had to break that symmetry to give the W and Z bosons their mass while leaving the photon massless. The answer came from a mechanism proposed independently by several physicists in 1964, but most prominently associated with Peter Higgs, a quiet British theorist working at the University of Edinburgh. Higgs proposed that there exists a field pervading all of space which interacts with certain particles and gives them mass. The W and Z bosons interact strongly with this field and acquire large masses. The photon doesn't interact with it at all and remains massless. The symmetry between the electromagnetic force and the weak force is real. It exists at the fundamental level, but it is hidden, masked by the Higgs field, which treats the different carrier particles differently and makes the two forces look very different at everyday energies. It's a bit like a perfectly smooth, symmetric lake that has frozen over unevenly. The lake itself is symmetric, the same in every direction, but the ice on the surface is lumpy, thicker in some places, thinner in others, and if you could only see the surface, you'd think the underlying lake was asymmetric too. The Higgs field is the uneven ice. The underlying electroweak force is the smooth lake.
In 1967, Stephen Weinberg, working at MIT, and independently Abdus Salam, working in Trieste and London, took Glashow's framework and incorporated the Higgs mechanism into it, producing a complete, self-consistent theory of the electroweak force. Weinberg's paper, titled A Model of Leptons, is only 3 pages long and is one of the most cited papers in the history of physics. It showed that electromagnetism and the weak nuclear force are indeed 2 manifestations of a single underlying force, related by a mathematical symmetry that is broken by the Higgs field. At low energies, at the energies of everyday life, the symmetry is hidden. Electromagnetism and the weak force look completely different. Electromagnetism is carried by massless photons and reaches across infinite distances. The weak force is carried by massive W and Z bosons and operates only at subatomic scales.
They seem like entirely separate phenomena, as different as amber tricks and lodestones seemed to Thales. But at high enough energies, at temperatures above about 10 to the 15th degrees, the kind of temperatures that existed in the universe less than a trillionth of a second after the Big Bang, the symmetry is restored. The Higgs field loses its grip. The masses of the W and Z bosons melt away, and the electromagnetic force and the weak force merge into a single, unified electroweak force, carried by 4 massless bosons that are all on equal footing. Glashow, Weinberg, and Salam shared the Nobel Prize in Physics in 1979 for this work, and in 1983, the W and Z bosons were discovered experimentally at CERN, the European Particle Physics Laboratory near Geneva, with masses almost exactly matching the predictions of the electroweak theory. Carlo Rubbia and Simon van der Meer won the Nobel Prize in 1984 for that discovery. And in 2012, the Higgs boson itself was discovered at CERN in the Large Hadron Collider, the enormous particle accelerator that straddles the border between France and Switzerland. The particle that gives the W and Z bosons their mass, the particle that breaks the electroweak symmetry and makes the electromagnetic and weak forces look different at everyday energies, was found exactly where the theory said it should be, with exactly the properties the theory predicted. That was the 5th unification. The electromagnetic force and the weak nuclear force, which seemed so different on the surface, one reaching across the cosmos and the other confined to the interior of atoms, turned out to be 2 low-energy faces of a single electroweak force, separated only by the intervention of the Higgs field. And if you step back, if you take in the entire arc of the story we've walked through tonight, the pattern is striking. Over and over, things that appeared separate turned out to be one. Static electricity and current electricity. Electricity and magnetism. Electromagnetism and light. Electric fields and magnetic fields. And now electromagnetism and the weak nuclear force. Every century or so, another wall falls, and the number of fundamental forces decreases by 1. In the 1800s, a physicist might have listed 6 or 7 apparently separate forces and phenomena. By the end of the 20th century, we were down to 3. The electroweak force, the strong nuclear force, and gravity. And the question that haunts modern physics, the question that keeps thousands of theorists awake at night and drives experiments at accelerators costing billions of dollars, is obvious. Can we go further? Can the strong force be unified with the electroweak force? And can gravity, that most stubborn and mysterious of forces, eventually be brought into the fold? There are theories that attempt the first step. They are called Grand Unified Theories, or GUTs. and they propose that at energies far beyond what any current accelerator can reach, the strong force and the electro-weak force merge into a single, grand, unified force. If these theories are correct, then at temperatures that existed only in the first trillionth of a trillionth of a trillionth of a second after the Big Bang, there were only two forces in the universe. The grand unified force, encompassing electromagnetism and the weak and strong nuclear forces, and gravity. And the ultimate dream, the one that Einstein spent the last 3 decades of his life pursuing without success, is a theory of everything. A single framework in which all 4 forces, gravity included, are revealed as different aspects of one master force. String theory, loop quantum gravity, and other exotic proposals all aim at this ultimate unification, but none of them has been confirmed experimentally. As of right now, we don't know if a theory of everything exists. We don't even know if the question is well posed. Maybe the universe doesn't have a single underlying force. Maybe 3 is the final number. Maybe the pattern of unification that has served us so well for 3 centuries will simply stop working at some point. But if history is any guide, and it often is, the pattern suggests otherwise. Every time someone has said, these 2 things are fundamentally different and can never be connected, they have been proven wrong. Electricity and magnetism are different. Wrong. Electromagnetism and light are different. Wrong. Electric fields and magnetic fields are separate. Wrong. Electromagnetism and the weak force are different. Wrong. The universe, it seems, is more unified than it has any obligation to be. And the fact that a human mind, working carefully, armed with nothing but mathematics and physical intuition, can discover these unifications, can peer behind the surface diversity of the world and glimpse the deeper simplicity underneath. That's one of the most astonishing things about our species. The transition from classical electromagnetism to quantum electrodynamics is one of the great intellectual dramas of the 20th century, and I want to give it a little more space, because it illustrates something beautiful about the way unification works. Sometimes, when you try to unify 2 theories, the result isn't just a combination of the original ingredients, it's something qualitatively new, something that neither parent theory could have predicted on its own. Classical electromagnetism, Maxwell's theory, describes smooth, continuous fields and waves. Quantum mechanics, as developed by Bohr, Heisenberg, Schrödinger, and Dirac in the 1920s, describes a world of discrete states, probabilistic outcomes, and particles that behave like waves, and waves that behave like particles. Merging these 2 frameworks wasn't like mixing 2 colors of paint. It was more like crossing 2 very different species and getting an offspring that surprised everyone. The offspring, quantum electrodynamics, turned out to have features that neither classical electromagnetism nor non-relativistic quantum mechanics possessed. The most dramatic of these is the existence of virtual particles. In QED, the electromagnetic force between 2 charges is not carried by a smooth, continuous field. It's carried by the exchange of virtual photons, ghostly particles that flit in and out of existence in the space between the charges, living for immeasurably brief instants, borrowing energy from the vacuum in a way permitted by the uncertainty principle, and then vanishing. This sounds wild, and it is, but it works. The calculations based on virtual photon exchange produce predictions that match experimental measurements to 12 decimal places. The vacuum of empty space, in QED, is not really empty. It is a seething cauldron of virtual particle-antiparticle pairs, constantly appearing and disappearing, a quantum foam that fills all of space and influences every charged particle in it. One of the most famous predictions of QED is the Lamb shift, a tiny difference in the energy levels of hydrogen that classical theory cannot explain. Willis Lamb measured it in 1947 using microwave spectroscopy, and it was one of the key results that spurred Feynman, Schwinger, and Tominaga to complete the renormalization program. The shift is caused by the interaction of the electron in hydrogen with the virtual photons and virtual electron-positron pairs that swarm in the vacuum around it. The electron is never truly alone. It is constantly surrounded by a cloud of virtual particles, and that cloud shifts its energy levels by a tiny but measurable amount. Feynman's approach to QED was, characteristically, the most visual and the most intuitive. His Feynman diagrams represent the interactions of particles as simple line drawings. An electron is a straight line. A photon is a wavy line. When an electron emits or absorbs a photon, the lines meet at a vertex. And the probability of any physical process, any scattering event, any emission, any absorption, can be calculated by drawing all possible Feynman diagrams for that process and summing them up. The simplest diagrams give the dominant contribution. More complicated diagrams with more vertices and more virtual particles give smaller and smaller corrections. And when you add up the contributions from all possible diagrams to whatever level of precision you desire, the result matches experiment to however many decimal places you care to compute. It is a theory of breathtaking precision and, in Feynman's hands, breathtaking elegance. Feynman himself described QED as the strange theory of light and matter. He wrote a popular book with that as the title, in which he explained the key ideas without using any equations at all, using only arrows and his diagrams. He was deeply aware of how strange the theory was, how far removed from everyday intuition. "If you think you understand quantum mechanics," he once said, "you don't understand quantum mechanics." But he also knew that QED was the most successful theory in the history of science, and that its success pointed toward a profound truth about the nature of the physical world. The electromagnetic field, when properly understood, is not a smooth, classical entity. It is quantized. It comes in packets. Its interactions are probabilistic, not deterministic. And the vacuum through which its waves propagate is not empty, but alive with quantum fluctuations. And the structure of QED, the mathematical framework of gauge symmetry that underlies it, turned out to be a template, a pattern that could be applied to the other forces. The weak nuclear force could be described by a similar gauge theory, with its own carrier particles, the W and Z bosons. The strong nuclear force could be described by yet another gauge theory, quantum chromodynamics, or QCD, with carrier particles called gluons. And the gauge symmetry connecting electromagnetism and the weak force, the symmetry that Glashow, Weinberg, and Salam identified, was exactly the kind of pattern that the QED template predicted. The electromagnetic force is carried by one massless gauge boson, the photon. The weak force is carried by three massive gauge bosons, the W+, W-, and Z. And the reason the weak bosons are massive while the photon is massless is that the underlying symmetry connecting them is broken by the Higgs field. Remove the Higgs field, turn up the energy high enough that the field releases its grip, and all four bosons become massless. All four forces merge, and the distinction between electromagnetism and the weak force vanishes. That is the electroweak unification, and its roots run all the way back to Faraday and Maxwell, through Einstein and Dirac and Feynman, to Glashow and Weinberg and Salam and Higgs. One continuous thread of human curiosity, stretching across centuries, asking the same question over and over. Is the world simpler than it looks? And getting, over and over, the same answer. Yes. Always yes. Let me fill in a few more details about the electroweak story, because the way the unification was confirmed is a remarkable piece of scientific detective work. The central prediction of the Weinberg-Salam theory was the existence of three massive carrier particles for the weak force. Two charged particles, called the W+ and W- bosons, and one neutral particle, called the Z boson. These particles were supposed to be extraordinarily heavy, around 80 to 90 times the mass of a proton, which is why the weak force has such a short range. A heavier carrier particle means a shorter range force, for reasons rooted in the uncertainty principle of quantum mechanics. The photon, being massless, carries the electromagnetic force to infinite range.
The W and Z, being enormously heavy, carry the weak force only across distances smaller than an atomic nucleus. Finding these particles required a machine of unprecedented power. The particles are so massive that creating them requires concentrating an enormous amount of energy into a tiny space, in accordance with Einstein's mass-energy equivalence. The machine that did the job was the superproton synchrotron at Kern, near Geneva, which was modified in the late 1970s and early 1980s to collide protons with antiprotons head-on. The collisions were violent enough to produce W and Z bosons, but the particles live for only about 3 times 10 to the negative 25th seconds before decaying into other, lighter particles. So the discovery involved not seeing the W and Z directly, but recognizing their fleeting signatures in the debris of the collisions. The experimental team was led by Carlo Rubbia, an Italian physicist of enormous energy and, according to almost everyone who worked with him, enormous difficulty. Rubbia was brilliant, driven, impatient, and not always diplomatic. He had championed the idea of colliding protons with antiprotons, which was technically daring and logistically nightmarish, because antiprotons are fiendishly hard to produce and store in sufficient quantities. The technical challenge of accumulating enough antiprotons was solved by Simon van der Meer, a Dutch engineer at CERN who invented a technique called stochastic cooling, which is a way of using feedback signals to calm the chaotic motion of antiprotons in a storage ring, gradually squeezing them into a tight, dense beam suitable for collisions. In January of 1983, Rubbia's team announced the discovery of the W boson. The Z boson followed a few months later. The masses matched the predictions of the electroweak theory almost perfectly. Rubbia and van der Meer shared the Nobel Prize in 1984, and the electroweak unification moved from theoretical prediction to established fact. But the story wasn't quite complete, because the Higgs boson itself, the particle associated with the Higgs field that breaks the electroweak symmetry and gives the W and Z their masses, remained undiscovered. Finding it became the central goal of particle physics for nearly 3 decades. The Large Hadron Collider, the most powerful particle accelerator ever built, was designed and constructed largely with this goal in mind. It's a ring 17 miles in circumference, buried under the Swiss-French border, in which protons are accelerated to nearly the speed of light and then smashed together head-on. On July 4, 2012, 2 independent experimental teams at the LHC, named ATLAS and CMS, simultaneously announced the discovery of a new particle consistent with the Higgs boson. The mass was about 125 times the mass of a proton. Peter Higgs, then 83 years old, was in the audience at CERN when the announcement was made. He wept. The discovery confirmed the final piece of the electroweak puzzle. The symmetry between electromagnetism and the weak force is real. It existed in the early universe, when temperatures were high enough that the Higgs field hadn't yet settled into its current state. And it is hidden now, at the low energies of everyday life, by the Higgs field, which fills all of space and gives mass to the W and Z bosons, while leaving the photon massless. So now the ledger looks like this. We started the evening with a long list of apparently separate phenomena: the amber effect, lodestone, lightning, compass needles, the voltaic pile, light, color, radio waves, radioactive decay, and through 5 unifications spread across roughly 3 centuries, we have reduced all of that to 2 fundamental forces. The electroweak force, which encompasses both electromagnetism and the weak nuclear interaction, and the strong nuclear force, which holds the nuclei of atoms together. Gravity stands apart, described by Einstein's general relativity, stubbornly resisting incorporation into the quantum framework that describes the other 3 forces. Grand unified theories propose that the strong and electroweak forces merge at energies far beyond the reach of current accelerators, energies that existed only in the unimaginably hot, unimaginably dense state of the universe within the first fraction of a second after the Big Bang. If these theories are correct, then in those earliest moments, there were only 2 forces: the grand unified force and gravity. And the most ambitious theories of all, string theory, M theory, loop quantum gravity, propose that even gravity joins the fold, that all 4 forces are ultimately one, a single interaction, a single rule, a single equation from which everything, the stars, the atoms, the light, the life, all of it emerges. We don't know if that final unification exists. We don't have experimental evidence for grand unified theories, let alone a theory of everything. The energies involved are so far beyond what any accelerator can produce that direct testing may be impossible for centuries, if ever. But the pattern is there. Every time physicists have looked for unity beneath apparent diversity, they have found it. And the universe has never turned out to be more complicated than it needed to be. There's a story about Richard Feynman that I think captures something essential about the spirit of this whole enterprise.
Someone once asked him whether the beauty of a flower is diminished by scientific understanding, whether knowing about cells and chlorophyll and photosynthesis takes something away from the aesthetic experience of looking at a rose. And Feynman answered that he could appreciate the beauty of the flower just as well as anyone, but that he could see deeper. He could imagine the cells, the complex biochemistry, the fact that the colors of the flower evolved to attract pollinators, which is itself a fascinating story. He could see beauty at multiple scales, and each scale added to the experience rather than subtracting from it. The same applies, I think, to electricity and magnetism. You can look at a compass needle and see a small piece of metal that points north. Or you can look at it and see a manifestation of the same force that produces lightning, carries starlight, holds atoms together, and merges with the weak nuclear force at temperatures that existed a trillionth of a second after the beginning of the universe. The second view doesn't replace the first. It enfolds it. It adds layers. It connects the small, familiar object in your hand to the largest structures and deepest principles of the cosmos. And I think there's something calming about that connection, especially as you're lying here in the dark, letting the day dissolve. The same force that is responsible for the most violent phenomena in the universe, lightning bolts, stellar explosions, gamma-ray bursts, is also responsible for the quietest, the faint warmth of your skin, the steady rhythm of your heartbeat, the soft glow of a nightlight, the gentle, invisible hum of the electromagnetic field, filling every point in space, holding your atoms together, carrying your thoughts from neuron to neuron, radiating your body heat into the cool air of the room. It's all one thing. That's the lesson of 3 centuries of discovery. It's all one thing, and that one thing is everywhere, and it is doing its work right now, as it has since the universe began, as it will until the universe ends, quietly, faithfully, without pause and without effort, holding the world together while you sleep. And the people who figured this out, Thales with his amber, Franklin with his kite, Volta with his stack of metal discs, Ørsted with his startled glance at a compass needle, Faraday with his iron ring and his notebooks full of imagined lines of force, Maxwell with his 4 equations, Hertz in his darkened room, Einstein in his patent office, Dirac with his elegant algebra, Feynman with his diagrams, Weinberg with his 3-page paper, Higgs waiting 50 years for confirmation. They were all doing the same thing, in different centuries, with different tools, in different languages, in different countries. They were all pulling at the same thread, and the thread kept going, and the world kept getting simpler, and the simplicity kept getting more beautiful. That's a good thing to fall asleep to, I think. So, here we are. You've traveled a long way tonight,
From a piece of fossilized tree sap on the coast of ancient Turkey to the vast underground ring of the Large Hadron Collider beneath the Swiss-French border. From Thales rubbing amber and wondering if stones had souls, to Higgs weeping in an auditorium as a machine 17 miles in circumference confirmed a prediction he'd made half a century earlier. And the thread connecting all of it, the thread that runs through this entire story, is unification. The slow, stubborn, sometimes accidental discovery that the world is simpler than it looks. That phenomena which seem completely different on the surface are, underneath, the same thing, viewed from different angles, at different scales, in different conditions. The crackle of a wool sweater on a winter morning, and the bolt of lightning that splits a tree. One force. The compass needle that guided ships across the Pacific, and the electric current that powered the telegraph lines along the railroads. One force.
The light of a candle, the warmth of a fire, the radio signal carrying a voice across the ocean, the X-ray that reveals the bones beneath your skin. One force. And that force, in turn, merges with the weak nuclear interaction that drives the fusion reactions inside stars, producing the energy that sustains all life on this planet. Every century or so, another wall falls, and the world simplifies. And every time it simplifies, it also becomes stranger. Because the connections are never the ones you'd expect. Nobody looking at amber and lodestone would have guessed they were related. Nobody looking at magnets and light would have imagined they were the same thing. Nobody looking at the electromagnetic force and radioactive decay would have suspected they shared a common origin. The unity is always there, but it's always hidden, disguised by surface differences, buried beneath layers of scale and energy and reference frame.
And right now, as you lie here in the dark, all of it is happening around you and inside you and through you. The electromagnetic field, that invisible architecture that Faraday glimpsed and Maxwell described, is threading through every atom of your body. It's the reason those atoms hold together. The electrons in their orbits are bound to the nucleus by the electromagnetic force. The chemical bonds linking atom to atom in the molecules of your skin, your bones, your neurons, your blood, are electromagnetic. The nerve impulses carrying signals from your brain to your lungs, telling you to breathe, are tiny electrical currents flowing along cell membranes, the same fundamental phenomenon that Galvani glimpsed in his twitching frog legs 2.5 centuries ago.
Your heart is beating right now, because a small cluster of cells in its upper chamber generates an electrical impulse, roughly 60 to 100 times a minute. And that impulse spreads through the cardiac muscle in a precise, coordinated wave, triggering contraction, pushing blood through arteries and veins and capillaries, keeping you alive. An electrocardiogram, when doctors tape electrodes to your chest, is measuring the electric field generated by this process. Your heart is an electromagnetic device, and the warmth radiating from your skin right now is electromagnetic radiation, infrared light. Photons, little packets of energy, streaming off your body at the speed of light, carrying away heat, obeying Maxwell's equations exactly as they were written 160 years ago. You are glowing right now in the infrared. A thermal camera would see you shining softly in the dark, a warm shape against a cooler background, outlined in electromagnetic radiation. The phone on your nightstand, if it's there, is quietly receiving electromagnetic waves from a cell tower somewhere nearby. Radio waves, Hertz's waves, the very same phenomenon he detected with a tiny spark in a darkened room in Karlsruhe, are passing through your walls, through your furniture, through you, carrying data, carrying voices, carrying the entire humming network of modern communication. And you can't feel any of it. The waves pass through you as if you weren't there, because your body is mostly transparent to radio frequencies. You are immersed in an ocean of electromagnetic radiation, an invisible sea of waves at every frequency. And you have been your entire life, and so has every human being who ever lived. The only thing that changed is that we learned, slowly, painfully, beautifully, to understand it. And beyond the walls of your room, the story continues. The light from the nearest star, Proxima Centauri, left its surface about 4 years ago and is still traveling toward Earth at the speed of light, still obeying Maxwell's equations, still carrying energy across the void. The cosmic microwave background radiation, the faint afterglow of the Big Bang itself, fills every last fraction of space, a remnant of the moment when the universe cooled enough for atoms to form, about 380,000 years after everything began. Those photons have been traveling for nearly 14 billion years, and they are electromagnetic waves. They obey the same 4 equations. They are made of the same stuff as the infrared glow of your skin and the spark from Thales' amber. There is something quietly magnificent about that, about the idea that the same physics, the same 4 equations, the same single force, governs the spark from a rubbed stone, the light from a galaxy 10 billion light-years away, and the electrochemical signals carrying your dreams tonight. That a force first noticed because a golden stone picked up bits of straw turned out to be the force that holds atoms together, carries light across the cosmos, powers the stars, and lets you see the face of someone you love. 5 unifications. 3 centuries of work, hundreds of scientists, some brilliant, some lucky, some both, stumbling and arguing and occasionally dancing around the laboratory when a new element appeared at an electrode. And what they found, piece by piece, is that the world is more unified than anyone had a right to expect. Maybe the pattern continues. Maybe the strong force joins the fold. Maybe gravity, that most stubborn and solitary of forces, eventually takes its place in a single, all-encompassing framework. Maybe someday, someone will write down one equation, a single line, from which everything in the universe can be derived. Or maybe not. Maybe 3 forces is the final number. Maybe the universe has a few irreducible pieces that simply can't be combined. We don't know yet. And that's all right, because even what we already know, even the unifications already achieved, are enough to leave you breathless if you sit with them long enough. The fact that amber and lightning are the same, the fact that magnets and wires are the same, the fact that light and radio and X-rays are the same, the fact that electromagnetism and the weak force are the same. Each of these is a victory of human curiosity over surface appearances, a moment where someone looked past the obvious differences and glimpsed the deeper sameness underneath. The electromagnetic field is humming along right now, in the wires in your walls, in the signals passing through the air,
in the bonds between atoms in your pillow and your blanket and the air you're breathing. It was here before anyone understood it, and it will be here long after this evening is forgotten. Faraday imagined it. Maxwell described it. Hertz proved it. Einstein unified it. And now you know a little bit about how it all fits together. You don't need to hold on to any of this. You don't need to remember the names or the dates or the sequence. Let it settle, the way sediment settles in still water. Let the facts blur and the feeling remain. The feeling that underneath all the complexity of the world, there might be something very simple. One force, one field,
One quiet hum, running through everything, connecting everything, holding everything gently together. The waves will still be traveling in the morning. The field will still be here. The atoms of your body will still be held together by the same force that moves compass needles and carries starlight. And that's enough. That's more than enough.